असं नको व्हायला की आपण एकदा एन्जॉय
We'll start in a moment. Please.
शकू. असं नाही झालं पाहिजे. हा तसं नाही झालं पाहिजे. त्याच्यामुळे आपल्याला करून टाकेल ब्लॉग. ती वापरूच नाही ती. स्कीम मधूनच करा. हो ना. असं होऊ शकते असं वाटते मला. मग काय ऑप्शनच नाही राहणार ना आपल्याला. तेच वापरा. कोडेक्स वगैरे आहे त्याच्यामध्ये. कोडेक्स ChatGPT पेक्षा डीपसीकच मला वाटतं. कोडिंगसाठी. मी अजून कोडिंग मध्ये गेलीच नाही त्यामुळे मी जास्त बघितलं नाही एक्सप्लोर नाही केलं एवढं. नाही पण तू तुला सांगत आहे शिकवून जातं. एवढं वेगळं काही घ्यायची गरज पुढे खूप खर्च करतात त्यात लोक पण आता त्या काय वापरते ते तिथे ChatGPT मधून मग कोडेक्स वापरते. ChatGPT मध्ये कोडेक्स येत राहते ना येत हो. म्हटलं मी कशाला मला जर भेटत आहे कोडिंग कशाला मी जर आपलं होत आहे तर मग कशाला नाही का जर फ्रीनी भागत आहे तर मग घ्यायची गरज नाही आहे आणि थोडंफार मग बघू गाईडकडे जाऊन काय होत तर स्मिता मॅडमला प्रॉब्लेम नाहीये तर तेवढे ChatGPT जिंदाबाद आहे तिचा थोडं मोठं नाही तिचे हसबंड पण आहे म्हणा आपण किती फरक पडते आपण गाईडला एक गोष्ट विचारायला एवढा विचार करतो त्याच्यात
मॅडम तुमचा
Please mute your microphone.
So let me welcome you all, and we would like to start. So I request everyone to keep their microphone off unless they're talking. So let me welcome you all, and we'd like to start. Sorry, there was an echo from the YouTube broadcast, and still people are joining, but soon the room will be full. And then when any of you find the full room is full, then you can join via YouTube link as well. So I request everyone to switch off their microphone, and when it comes to their turn to speak, please switch on your microphone. And so to begin with, it's my pleasure to welcome you all on behalf of JP Institute of Information Technology in particular and quantum information and community in general. So this is a very specific kind of program which we started from the last year, International Young Quantum Scientist Meet. And last year the response was very good. So that encouraged us to do the exercise once again. And this year we received 475 application for participation and about 100 abstract for presentation, out of which, because of the many were good, those which are not selected, it does not mean that they were bad, but we had a So can you hear me now?
Yes, sir. Yes,
Okay.
sir.
So I guess there was a power cut here, and I'm not visible, but I'm probably audible. Uh, so now everything is fine. So what I was telling that we had very good response last year, which encouraged us to continue this exercise for this year. So this year there are 475 applications for participation, out of which 80 people, little more than 80 people submitted abstract. And this is excluding the people from our group and collaborators. So altogether, it was close to 100, and 44 papers have been selected for presentation. And the participation is from 29 different countries. So it's a very good representation of young quantum information community, and it's very nice to see the community growing. And community is growing not only in the direction that the young people are joining. There are many senior scientists who worked on different field, and they are also taking interest and joining our community. And it's expanding in all sense, means in the sense of depth, also that newer and newer results are coming, the beautiful aspects of quantum information are appearing, and we are sure that many such aspects will be reflected in the talks. I request everyone to restrict to time. So all the speakers will speak only for 15 minutes, and 5 minutes will be there for question answers. And please keep your microphone off unless it is your turn. So having said the so, and welcoming you once again, now I would like to request Professor H.S. Mani, who is lately taking much interest in quantum information. He was a director of HRI, which has eventually become one of the most prominent center of quantum information in India. And beyond that, he was teacher of many of my teachers. And same is true for those young quantum scientists, especially those who are from India and are part of this event. So I would like to request Professor Mani to say a few words and declare this conference as open, and then we move for technical session. Professor Mani, over to you. Sir, unmute yourself.
Am I audible?
Yes, sir.
Thank you, Anirban, for giving me this opportunity to speak to a large number of people. I see almost 90 people, and all of them actively working in various different areas. And I can say that I have seen the kind of progress Indian scientists, doctors, various academicians have made over the last 6-7 decades. Let me just give you an example. I was very happy that I could solve the problems of Jackson. So I was mentioning this to one of the students. He said, "Sir, that's fine, but can you write a book like Jackson?" So that made me feel that we have a long way to go. We should not just be happy by doing a certain amount, which is very good, but the next step is necessary. And this is going on in our country. And I think it is one of the best things that can happen. I now see that the kind of cooperation that is happening between different disciplines is just enormous. As anyone knows, I have a couple of friends, Lakshmi Narayan and Shyam, whom I met accidentally. One works for Google, one works for Hewlett Packard. They are now learning not only quantum machine learning, they are also having projects where I am now working, Chennai Mathematical Institute, and I am enjoying their work. And at one stage, Lakshmi Narayan came and said that we should be able to make our own security codes. That's the minimum I can do for our country. This is the attitude with which I am sure most of you are following. And let me again briefly mention that I would like to listen to all the lectures. And if the abstract is sent to me earlier, I will be very happy and I will appreciate that. Thank you and the best for all of you.
Thank you, sir. And thanks everyone for joining in the right time, and we are on time. So now I would like to request Dr. Sandeep Misra, who is our colleague at JP Institute of Information Technology, is also a young quantum scientist, to work as the session chair for the first session of Young Quantum Scientist Meet 2026. And over to Dr. Sandeep Misra, and I can see the next first speaker, Chiranjeev, is already there. And Professor Mani, for your information, Chiranjeev did PhD from HRI, and he was a student.
But I was too young. So Professor Mani left like long back before even I joined
Chiranjeev was
HRI.
a student of Arun
So
Gandhi and completed
yeah.
PhD from. So anyway, over to Sandeep.
So thank you, Professor Pathak. So I think since the session is tightly scheduled, so let us not waste our time. So as far as this session is concerned, this session is dealing with quantum computing, and the first speaker of this session is Dr. Chiranjeev Mukhopadhyay from UESTC Chengdu, and his title of the talk is Quantum Reservoir Computing for Time Series Predictions. So Chiranjeev, if you are here, you can share your screen.
Thank you. So the screen sharing is disabled. Can you just enable it for a while? Whoever has the hosting permission, please like enable to.
Professor Pathak, can you please enable the screen sharing?
I'm trying. Just give me a moment.
Yeah. So while that is being done, let me just introduce what I'm trying to do, because I'm not really a quantum computer scientist in that way. So I have been like starting out to work on this reservoir computing, a new area for me. So I want to justify why I'm doing it first of all. So basically the point is that I mean, you have all heard about these variational quantum algorithms and Niskara quantum devices. Most of you have heard about, and I'm pretty sure that we will have like plenty of talks on these devices coming up. So, I mean, if you look at the headline kind of things, the Google experiment was just before COVID. I remember this Sycamore one. And then from then on, I mean, the number of qubits has increased from like 50 qubits to 100 qubits to now we have like close to 1,000 qubits. So, I mean, this whole Niskara was basically, you are saying that you are having qubits, which are essentially very fragile. But I mean, they are qubits nonetheless. So they live for far less amount of time than we would like ideally for them to live. But nonetheless, I mean, these are the qubits that we are trying to scale up. Now, when people were starting out experiments on this, I mean, kind of big experiments with big national players like Google or in China, in USTC, then the motivation was that we should be able to do immediately something useful with these
It is done and
qubits. Even if this cube, yeah, is it allowed now?
Yes, yes.
Oh, perfect. Okay. Can you see my screen?
It's coming.
You can see the screen now, is it?
We can see
I
your
can see
screen.
my name in your screen.
Can you please share your whole screen?
Yes, means now.
Yeah.
Now it's coming.
This is better, right? Okay.
We can see a lot of food.
Yes.
Okay, yeah. So this is the group. Yes. So the forecasting of this group is actually pretty nice because there is a lot of food on the table. So now, when people were doing this Niskara quantum computation stuff, and right now, globally speaking, we are in like the early fault tolerant era that we have a few qubits which are sort of immortal. You can think of it this way, and a lot of qubits which are basically noisy. But then during this noisy era of, Niskara of quantum computation, roughly what happened was that initially kind of our hope was that we will be able to do something immediately useful with them. Useful in the sense that practically useful tasks. Boson sampling, etc. I mean, these tasks were kind of made up to show supremacy. But then for practically useful tasks, we kind of understood that the algorithm on which we kind of had the most amount of hope, these were like the family of variational quantum algorithms, they have their own shortcomings. In the sense that if you are thinking of like classical neural networks, then you have to adjust every weight at every node, every connection. So I mean, this is kind of, I mean, this requires a lot from the system physically. And then the heavy optimization is handled with the classical optimizer. So the point is that you have to train all these connection weights and these. I mean, you can write them down on a piece of paper, but if you are looking at real hardware, so there are leaks and slippages and everything that can happen. And number two, what people realized after 2 or 3 years of doing this is that this is so the optimization of this neural network. I mean, it has some inherently bad features. These are called barren plateaus, and I'm pretty sure you will hear about them later on. But all it means is that we have a bunch of these Niskera quantum devices, globally speaking. We have gone up to 1,000 or so qubits. And then in India, we are just starting out research on these Niskera devices. So right now, I mean, there are lots of different platforms, and in each platform, we have small devices, 6 qubits, 8 qubits. I mean, it does not mean that we are not making progress. We are making real progress. But the point is that we still have a long way to go. And the next important part is that if we go to like 8 qubits towards 1,000 qubits, which is basically the goal of this NQM project recently, then we have to figure out a way of making these things work, because we have built these things, but the first guys who built these things, they had a concrete idea that what they wanted to do. But it turned out to be a lot more difficult than they initially thought, or hoped at least. So for us, once we build these Niskera devices, big ones, then we have to put them to some use. It's not like enough to just put them on museums and to move on to the next one, right? So there has been a lot of money sunk into this, so we better justify it, right? So then VQA and variational algorithms, I mean, these barren plateau issues, I mean, they kind of present not a very good picture with these. So we have to urgently think of new algorithms, new kind of stuff that we can do software-wise, what is kind of more supported with noisier Niskera quantum devices, as well as that can do something useful, not merely proof of principle of some made-up task. Okay. So in this context, people think about quantum reservoir computing. So the reservoir computing, the idea is very simple. I mean, think of like a bucket. Okay. So if you have a bucket of water and then you drop bit by bit some ink particles into the bucket, some blue ink, some black ink, some yellow ink, something, and then you have a tap right at the end of this bucket, then you are opening this tap and figuring out what kind of things are there that are falling out of the tap. Remember, in the bucket, this blue ink, this yellow ink, this red ink, they kind of all mix together. So whatever you get out of this tap, you can analyze these things, and then you can see whatever has gone on or whatever computation this bucket is doing. Okay. So what it means is that these kind of stuff, the reservoir itself, we have no control over. I mean, we know the Hamiltonian, we know roughly how it evolves, but we cannot have specific individual control over what these things are doing. Okay. But our goal is to basically have whatever output that is coming out of this reservoir. I mean, for this quantum case, we will be measuring on some output layer qubits. And then from that, we want to reconstruct back some result, which we want to basically fit to get some information, some knowledge about whatever input has gone in, and then we can use this as a training algorithm. So the training happens only at the output layer, not at every layer inside. So this is like the first advantage over these variational quantum algorithms. And then these the reservoir, inside the reservoir, whatever happens, I mean, it's a very disordered, a very messy kind of system. So it is not necessary it has to be quantum. I mean, the idea started from very classical roots. Then, I mean, but you do not bother about these things. I mean, you have no control over these things. Okay, fine. I mean, you just let go. You just train over the output layer. Okay. So this is reservoir computing. And if the reservoir itself, I mean, consists of quantum particles with quantum interactions, then we call them quantum reservoir computing. So then what can we do with these things? I mean, first approach, which is a very theoretical approach, is that we kind of propose all sorts of reservoirs with different kind of platforms and everything what we can do. But the second approach that I'm going to be talking about today, one particular application of it, is using reservoir computing for time series predictions. Now, time series predictions, if we think of it this way, time series predictions, I mean, time series datasets are everywhere. You can have time series datasets in ECGs, for example. You can have climate data. You can have stock market data. You can have basically time series data are everywhere. I mean, whatever you look at mostly are like the x-axis is some time, right? So then if we can predict based upon previous time series data points, what the next data points would be, that will be, I mean, I do not need to say that will be an incredibly useful thing to do. I mean, if you can predict what the stock market is going to be tomorrow, you can make a lot of money, right? So what we try to do in this project is we try to predict the realized volatility which is basically how much a stock market index or a stock or something, whatever, something that fluctuates. Realized in the sense that we are not looking at the future, we are looking at the volatility that has already been there based upon the past data. Okay, so what the data set that we have is S&P 500, which is like the standard American stock market index. And we are looking at monthly volatility data from 1950, which was just before World War II, up until 2017. So it's a huge amount of data, monthly data. And then based upon, I mean, we are trying to train on 1950 to around 1997. And then for the next 20 years, I mean, this is your test, essentially. You want to see how good this reservoir computing thing performed. Okay, so what people normally do for prediction, if you ask like a finance professional or like somebody who does work on this Wall Street kind of things, so they will tell you that one approach, which is more like kind of economics approach in some sense, is that we want to build models. So I mean, it is obviously familiar to physicists as well that we want to build models, right? So for them, the model is what kind of underlying ingredients go into the volatility. So there can be lots of sources of volatility. There can be very short-term kind of sources of volatility. Suppose something like whatever Trump tweets. There can be kind of intermediate-term sources of volatility, like weekly. Say that in Nifty, you know, some of you who trade, you know that Nifty has weekly expiries. So the volatility kind of goes up every week at that expiry day. There is monthly volatility. So that is, I mean, volatility which has a longer path cycle. For example, I mean, if you look at the stock market data or something, then every month, whenever these salaried people, they get money, they put some money into the stock market, many of them. So that means that there is a volatility associated with the beginning of month, essentially. So there are all these sources of volatility which have different time scales. So you can basically build a model where you incorporate these time scales, the different volatilities at different time scales as like your contributing factors, and you can have some weights attached to each of them. And then all of your task is basically look at your past data and fit the coefficients or these weights of each individual contribution. This is the simplest possible kind of model building exercise that you can do. So then you can also incorporate other factors, which are macroeconomic kind of indicators, dividend yields or like bond yields or whatever industrial production has gone on, etc. So you can incorporate those things into this model as well. But the key point is that this is model building, and all we are looking is that using the past data to fit the curve. So this is one approach that is very respected in financial circles. So for example, I mean, this model that I'm talking about, this is called HAR, heterogeneous autoregressive models. So now the second approach is that, okay, I mean, we have talked about model building, which is essentially curve fitting. The second approach is that we are going to be using machine learning. So for that, for machine learning, if you think of it like typical machine learning architecture, so the first one, the simplest possible kind of the simplest possible kind of architecture is feed-forward kind of neural networks, where you have a kind of one-dimensional flow, but there is no feedback. I mean, kind of, this is useless for time series predictions. As, for example, in MNIST or something, you do not care about in which order the pixels are filled. But in time series data, you absolutely have to care. What volatility comes before that, once volatility comes after that, you absolutely have to care about these things. So then the recurrent neural networks, which are basically neural networks based on feedback, so these neural networks become useful. So for example, LSTM is like one particular example, which is like very highly used in industry as well as many other tasks. And the third approach is reservoir computing. So basically, we are putting in this input data, past data of whatever the financial quantity was there, and then we are trying to learn on the fly, essentially, what the next value would be. This weight matrix that you see, so what is going on here? So this output that you see, this HT, so it can be in classical reservoir computing, it can be like an output layer. In quantum reservoir computing, it can be measurement results. This is what I'm going to be discussing. And then these measurement results, these are connected to eventual predictions with respect to some weight matrix. This weight matrix is something that you have to train based upon only the output layer, not on all layers. So once you have trained this weight matrix, then you can feed, I mean, you can feed basically any HT, any input state into it to get whatever output prediction that you will get. So this is roughly the approach of doing things. Now in the quantum architecture, we have I mean, we are looking at the most general kind of architecture where you have input states which you are putting in. And also you have a bunch of features which you ideally want to put in. And then you have a few other qubits, which are basically the bulk of the reservoir. So think of it like this, that you are putting in oil droplets or like ink droplets into your reservoir, and the reservoir is the rest of the hidden qubits, which kind of allows interaction. The whole thing is a kind, I mean, for us, we took a transfer sizing model or to all kind of couplings. Yes, hello? Okay, so
Ranjan, do you have any question or you can mute yourself? Yeah, Chiranjeev, you can continue.
okay, so for this quantum reservoir kind of architecture, what we have is that you have the hidden qubits. I mean, we call it hidden because, I mean, they are not used for encoding or anything. The rest of the qubits we encode, and then we allow these qubits to mingle with respect to this Hamiltonian. And then once we mingle it enough number of times, so the information essentially percolates from the encoding qubits, the information that we have encoded, the previous data, into all these hidden qubit things, because it has evolved and everything is coupled with everything else. And then finally, we want to recover this amount of information that we originally put in, and then we train our weight matrix according to recovered information, which we get from the measurement results. So for us, the training data is like 1950 to 1997, and the reservoir, as I mentioned, is just a transfer sizing model with fully connected kind of couplings. And these couplings are random because we do not assume that we have any control over them. This is the whole point after all. But these couplings are also fixed. So these couplings are not like changed at every iteration or whatever. Once we have fixed them randomly, we can keep going with this. And then we can also encode instead, in addition to previous data, we can also encode some features which are like dividend ratios, the price earning ratios, as you know, kind of other the econometric factors and everything. And then we want to investigate which features are the most useful, or which features contribute the most towards realized volatility prediction. So remember, I mean, this model, whenever we are building models, so we necessarily have to truncate somewhere, because otherwise we will have an infinite number of parameters to fit. Even here, so we can have only a finite number of features, because in principle, quantum reservoirs can be large, but in practice, I mean, whatever we have, we are doing it in a classical computer after all, then the reservoir has to be quite small. So we have to, we cannot incorporate all these features, then there will be no more hidden qubits to exploit. So we have to take a choice. And this choice is essentially done by something that we call a wrapper method, but this is getting technical. But the result that we get, I mean, this QR1 and QR2 are kind of technical terms I will explain in a moment, but let me just get back to the results we get. The result we get is that, I mean, lower is better. This is mean square error. So we want this error of prediction to be lower. So if we only incorporate the data from past data, the past data on realized volatility, then the error is like, I mean, it's low, but it's not that low. We can do better. But then if you have these features, so MKT is market excess return. You can look at the definition. So this is basically return of stock market index minus the return of T-bill rate, which is the risk-free rate. So if this is the most important feature after realized volatility, after past data, then you can have dividend rate, then you can have investor production. So you have a whole sequence of features which are more or less and getting less and less responsible, etc. But you see, and similarly for QR2 is basically an ensemble learning method where you have the same reservoir learning algorithm, but then you have two slightly different reservoirs, essentially. Slightly different in the sense that in the last step there is like a multiplexing happening, and then we use both of them to get some prediction. So that, I mean, we can have an even better prediction compared to a single one. Okay, so, but in both of them, see, one interesting thing is happening. That initially, if we encode more and more features, it is getting better and better. Of course, I mean, these features will contribute, right, to prediction. But after a while, after you have encoded 6 or 7 features, what happens is that, see, here, if you encoded all these features in these orange qubits, then the hidden qubits where the information percolates down to, we are down to very small number of hidden qubits. So information cannot be percolated down too much. So we have encoded too much information in the system. So the prediction accuracy kind of goes for a toss. So you initially improve a lot, but because you have less number of qubits, we have only 10, 12 qubits, after a point, I mean, it kind of becomes redundant. There are simply not too many qubits in the reservoir to play with. So this is something that we see. And this is kind of the fit between the actual data, actual test data, and whatever data we have, I mean, prediction we have with 1 feature, with 4 features, with 7 features, with 9 features, etc. So you can see that 9 features is not necessarily better than 4 features, at least visually. We have already seen this in terms of MSE. So now, I mean, the most important part that I will come to is what is this error that we get? So we basically compared reservoir computing, and remember, this is only 12 qubits. We can do it in practice. If we have an ISK device which has 1,000 qubits at our disposal, we can do a lot better. But at 10, 12 qubits, where we are doing these classical simulations, we have to stop at some point. This is 10, 12 qubits for us. See the results. So the result that we get from curve fitting kind of models, which are HAR and HARX, so lower is better. Okay. So then these results are like 0.14, 0.15. So think of it like 14%, 15% error something. This is ARMA. This is another method which is kind of curve fitting-ish, but in a stochastic way. So this is 13%, 11% something. LSTM, if you compare, which is a machine learning algorithm, classical machine learning algorithm based upon recurrent neural networks. So LSTM has like 13%. LSTM-X, which is LSTM plus additional features, this gives 11, 12%. And people have done research work on these things. So these the numbers we are taking, all these numbers are taken from our own benchmarking simulations, but similar numbers have been obtained in other papers in financial econometrics as well. And then this is classical reservoir computing. Classical reservoir computing gives 14% and reservoir computing with features. Classical reservoir computing with features. This gives us 10%, 11% kind of error. But now look at what happens with quantum reservoirs. So I say that this is a shitty reservoir. This is a 12 qubit reservoir. We can have disk devices which are much, much bigger than this. And even then, we have some prediction error, which is of the order of 10%. So, I mean, of course, so for us, it does not look like much to reduce from 12% to 10%. But remember, I mean, these are financial data sets. There are a lot of money riding on it. So even a small amount of improvement would be basically useful in a lot of sense. And then
Chiranjeev,
the similar kind of...
Sorry to interrupt
Yeah.
you. You have 2 more minutes. Yeah.
Okay, for sure. I'll be done.
Yeah.
So, and you can see similar kind of phenomenon happening with Q-like, which is basically another essentially figure of merit, kind of error of prediction. Lower is better again. And we see the same thing happening again. Okay. Now, these are the results for S equal to 1. That is, if we are predicting one step at a time. So that this is a monthly volatility chart. So we are predicting, I mean, based upon the previous data, we are predicting the next one's realized volatility. And this is the kind of result that we get. And if we want to predict 5 steps in advance, that is, I mean, suppose that we have data until March, March is going on. So data until like end of February, then we want to predict what should be the realized volatility in July. So for that, of course, I mean, it is like much worse because we are predicting some steps further in advance. But even then, you see that classical reservoir computing performs the best here. So 15% something, there is no way around it. But look at kind of how close the quantum reservoirs are. So this is like, again, 15%, almost touching. And then we have a bad reservoir. As I'm saying, we have a 12 qubit reservoir where it is in practical cases, if you have an actual reservoir of Niskera devices, which is like sufficiently big, 100 qubits, then 12 qubits is nothing. So MSE, you have 15% error. And then in Q-like, you have a kind of basically error which is almost close to the best one otherwise. And see how badly that typical kind of other methods that people use, LSTM or HAR, they perform compared to quantum reservoirs, even with a small reservoir. So this, I feel that there are some interesting things that can be done with quantum reservoir computing. And most importantly, these are things that can be done with Niskera devices. So this is one approach. And also, so if you look at time series prediction for other tasks, not just financial kind of data sets, if you look at time series prediction for chaotic maps, then we have another paper that I was supposed to talk about, but I do not have much time. And then we are also working on chaotic flows and like other kind of continuous evolution things. And they also show like very reasonable progress on this until now. So thank you.
So Chiranjeev, very nice talk. So I think we can take one or two questions. So if any, if there are any questions, please unmute yourself.
Unmute and ask question. And if there are questions
Uh,
beyond the time, then you can type in chat also.
hello, sir.
Sure.
Please continue.
Hello, sir.
Yeah.
Hello. Hello,
Please
sir.
answer
It's
the
me.
question.
Hello.
Sir, actually, you mentioned the quantum reservoir computing can be used for time series prediction and signal processing. So, can we
Yes.
use in the chaotic system, which is also highly dependent on the past states?
Yes. Actually, this is what I was going to say. So we have used it in chaotic systems. Actually, we have a concrete project running. I mean, sequence of works. So we have looked at chaotic maps, which are essentially chaotic discrete dynamical maps, like logistic maps or Henan and this kind of stuff. This is the simplest possible, and we see very good results. That it is basically whenever the system is chaotic, we can see lots of interesting physics. Whenever the system is chaotic, then the prediction is kind of bad, which is expected, but we can still predict up to a number of steps. We can still predict, and the most important part is that the amount of basically the size of the reservoir. This determines if you have a big reservoir, then it seems that we can predict lots of steps ahead in advance. Then we are looking at chaotic flows right now, which are basically chaotic continuous systems like partial differential equations, which are chaotic, and they also seem like to follow similar properties. So yeah, we're doing work on this. This is a really interesting thing to work on. Thank
Sir,
you.
actually, I asking just like you, we did in class chaotic system using quantum reservoir computing. So how can we simulate? Because we have very less qubits, and let us suppose we have an n-dimensional chaotic system. Like we suppose we have an n-dimensional chaotic system which is discrete. So there is a paper.
Keep the question short, and Chiranjeev, you can take this question along with the question in chat room. With about 12 qubits, can they get positive feedback if run using simulators? So you can address probably both together.
Okay, what about 12 qubits? Can they get positive
Sure.
feedback if run using simulators? Okay, this is a very interesting question. So, I will say that we have not run it using simulators in terms of actually this IBM's real quantum computers and everything. We have run everything on a laptop. And so, obviously noise issues have been neglected. So can we get positive feedback? I do not know.
Okay, thank you. I think
Thank you, sir.
the other questions can be emailed to Chiranjeev, or you can email to us also, and we can email to the Chiranjeev. So I think let us thank the speaker and move to the
Thank you.
next speaker of the session.
Thank you. Thank you.
Should I get started?
Shall they introduce the next speaker? Please tell the name and affiliation.
Oh, sorry. I was muted. So yeah. So next speaker of the session is Dr. Ritajit Majumdar, and he is from IBM India Research Lab, and his topic of the presentation is low overhead circuit cutting with operator backpropagation. So Ritajit, you can share your screen.
Yeah. Okay. Thanks. Yeah. I hope this is visible.
Yeah, it's
Yes,
visible.
it's visible, but you are not visible.
Oh, okay.
Yeah, I've not seen you for long, except outside the social media.
Yeah, sure. Let me turn on my video. Okay.
But now you are visible, slides are not.
No, the slide will come soon.
Fine. Everything is fine. Please continue.
Okay. Yeah. Thanks a lot for having me here. And
But make full screen.
It's in presenter view. We are seeing the black stuff.
Oh,
Make full screen.
wait. Why is that happening? Is it better now?
Yes. Everything is fine. Please continue.
Yes,
Okay.
it's fine.
So thanks a lot for having me. And the topic of today for me is scaling circuit cutting with operator backpropagation. And this is a work with Debarti, who was a summer intern with me last summer. at IBM, and she also has another paper to present this Thursday, I think. So I'll jump quickly into it. And first, let me talk about what is circuit cutting, and then I'll talk about the motivation of why we want to think of circuit cutting, although it immediately has some disadvantage. So if we think of, say, a classical circuit, so we have say, a 4-bit classical circuit, and say I have a system which can only operate on 2 bits, not 4 bits. So can I compute this classical circuit there? We can, of course. So I can just take this part separately, and I'll put in AB, I'll store AB, the outcome AB somewhere in some register. I'll take this part separately, I'll store BC in some register, and then I'll start this particular gate again, where AB and this B bar C will be my initial inputs, and then I can just compute the outcome as required. So instead of a single circuit, I need to run 3 circuits, that's fine. But I can very easily actually do a 4-qubit computation on a 2-qubit machine. Now let's try to think of a quantum version of this. And here, if you see, I have a quantum circuit, some random quantum circuit, and we immediately see the problems here. Let's say I want to do the similar kind of cutting, and I have this part as my quantum circuit. Starting with Q0, Q1 is not the problem. The output in general is a density matrix. How do we store the output? The same goes for the second. And even if there is some way to store this density matrices some way, how do I initialize this third circuit as those 2 density matrices? So although running a 4-bit classical circuit on a 2-bit quantum computer was very easy, running a 4-qubit quantum circuit on a 2-qubit quantum computer, it's not at all trivial, and there are many different problems that we can get into here. But still, we have something called circuit cutting here. And the idea here is that if you want to remove something, you need to consider a sort of tomography here. And therefore, you need to measure the circuit and prepare the circuit. You need to measure the circuit in a tomographically complete basis. And you need to prepare the following subcircuit. Say this is measured in different I, X, Y, Z, all sort of basis. And the corresponding subcircuit here will be prepared in the eigenstate of the basis of measurement. Similarly, we can do a gate cutting as well. And that gate cutting basically leads to a quasi-probability distribution. You can write down a 2-qubit gate as a linear combination of single-qubit gates and measurement, where the coefficients are guaranteed to add up to 1, but not necessarily all of them are between 0 and 1. So it's a quasi-probability distribution. And by doing so, you end up with something called a sampling overhead. That means when I cut this circuit, it is no longer just that I run this subcircuit and this subcircuit. I need to run it for different bases or different gates and everything. For gate cutting, that turns out to be 6 for each gate cut. And for wire cutting, that turns out to be 16. These are mathematical upper bounds. By doing some tweak, you can reduce that. Those are fine. But that's kind of the scenario of cutting here. Now, knowing that this kind of problem, instead of a single circuit, I need to run 6 circuits or something, why do I still want to opt for circuit cutting? Because each subcircuit has fewer gates and or qubits, either both or at least one of them, definitely. Therefore, each of these subcircuits will be less prone to noise. They will experience less noise. And then the final reconstruction, one point is that reconstruction can never be the final state because we are losing certain information, but the information that is retained here is sufficient to calculate expectation values. So if you are interested only in expectation values, this is great. Not at all if you are interested to retrieve the final state of the system. So the reconstruction of the final expectation value is classical. Therefore, the overall effect of noise in the system is less. And there are multiple papers on showing circuit cutting working as an error mitigation technique. I have cited 2 of my works, but there are many more. So here you can see a VQE case that we did with IISc 2 years back. And here also you can see that even after applying error mitigation versus if I apply circuit cutting, it goes much better. This is actually a 100+ qubit Ising model with periodic boundary. And here you see if you cut that periodic boundary and repeat the circuits the way we just discussed, you can get a significantly better result than the uncut scenario. And there are many, many more. So we like to think of circuit cutting as an error mitigation technique and not necessarily as a technique where you can run bigger circuits on a smaller device, because today we have pretty big devices, bigger than we know what to do with in some sense. We already talked about the limitations of circuit cutting. So let's say I'm cutting this gate and it will incur, like I need to run 6 circuits because I have cut this gate. Now, if I have 2 gates which I am cutting one after another, then I will require 6 times 6, so 36. It keeps on increasing exponentially. So naturally, what happens is, if you think how bad this is a Hamiltonian simulation circuit of a simple Hamiltonian. And if you want to cut this, it will end up requiring 3 wire cuts. And now you will have to execute 1500 plus circuits, whereas you could have just executed 1 circuit. So naturally, all the studies of circuit cutting, you will see, they are restricted to very small toy problems, and people almost kind of agree that this is a nice method which is not scalable because of this exponential overhead. Now let us switch gear completely and talk of something called operator backpropagation. Here also the idea is that we want to reduce the noise in the system by absorbing some part of the circuit into the observable. So again, we are dealing with scenarios where we want to calculate expectation value. So let's say I have a big circuit and I have a observable O. I can logically, so there is no physical cut here. I am logically partitioning this circuit into, say, a quantum portion and a classical portion. And now I can evolve this operator and I can absorb this part of the quantum circuit into the observable, and naturally the observable will evolve and it will update itself like this. So now we are left with an updated observable and a smaller quantum circuit. So naturally we expect this quantum circuit will be less noisy compared to this entire quantum circuit. This is the holistic idea of operator backpropagation. You trade off some classical overhead to do this evolution for reducing the noise in the system. Now, I won't go through all of these, but you can understand that these operators are Pauli. So if you have a entirely Clifford circuit, then you can just keep on doing backpropagation without much of an overhead. And you could just go and backpropagate through the entire circuit and nothing changes. I mean, all the Paulis, it just evolves to another new Pauli because Clifford gate maps a Pauli to another Pauli. So it is basically the same thing as saying that Clifford circuits are easy to simulate. But if you now think of a general circuit where there are some Clifford gates, some non-Clifford gates, then there is some paper which shows that if you have a non-Clifford gate where, say, you can write it as this e to the power minus I theta pi, where pi is a Pauli, of course, it's a generator of this. It need not be a single Pauli, of course, it can be tensor product of many Paulis. And you have the observable, which is also a Pauli. Then when you try to backpropagate, you need to identify whether P and O commute with each other or anti-commute. If they commute, then again, you can just backpropagate without having any issues. But if they anti-commute, then the observable basically forks into 2 parts which do not commute with each other. What this means is, if we take a generalized circuit here, once more, I won't go through the detailed calculation, but you can see if we have a generalized circuit here where I have logically partitioned it into 2 parts and I have some non-Clifford gate here now, this observable splits into 2 parts and now you are left with 2 smaller circuits and 2 different observables which don't commute with each other. That means now to calculate the expectation value, I need to run this circuit separately and this circuit separately. So instead of running a single circuit, I need to run 2 circuits. Worst case scenario, if it keeps splitting on every layer it backpropagates, it basically scales exponentially. In other words, what it says is that simulating a quantum circuit is exponentially hard. In some way, it is saying the same thing. Now, what we proposed in this work is, the proposal is very simple. You have a circuit, you first backpropagate the circuit. And when you backpropagate the circuit, you can expect that some of the cuts required in the later part of the circuit will get absorbed. Those parts of the circuit will get absorbed into the observable, and therefore you can just do away with it. So when you cut the circuit, now you require lesser number of cuts. And remember, it gives an exponential overhead. So even reducing a single cut can be significantly good. But let's take an example. The idea is simple. So here, if we have a 2-qubit Hamiltonian simulation kind of circuit and no backpropagation, I have just taken a simple observable like this, which is an average of all weight 1 Z-type observable. If you do a normal circuit cutting here, it will require 2 gate cuts, 1 wire cut. If you remember, sampling overhead of gate cut is 6, so 6 square, and sampling overhead of wire cut is 16. So you need 576 circuit executions. On the other hand, if I slightly backpropagate the circuit and can absorb this part into the observable, now I need only 2 cuts. But the way the observable splits, it now splits into 2 groups, which are like these 2 groups anti-commute with each other. Everything within the same group commute with each other. So I need 1 circuit execution for calculating the expectation value of these terms, 1 circuit for these terms. So now I have 6 times 16 coming from gate cut, wire cut, 2 circuits as such. So 2 times this. So I immediately jump down from 576 down to 192. That's a 3x reduction. And if we think of it in a more holistic way, when I can reduce the number of cuts, I do an exponential reduction in the number of circuit executions. But when I am doing backpropagation, it increases the number of non-commuting groups, which increases multiplicatively. So I need to have a sweet spot where this multiplicative increase is less than equal to the exponential reduction. How do we find that? I'll come to that. Let's show you some particular results. This is something we showed on 6-qubit VQE circuit, where the answers was this efficient SU2. The number of cuts can be reduced from 432 down to 144. And you can see that, as we said, circuit cutting itself acts as a error mitigation technique. So circuit cutting here itself is producing better result than uncut, noisy. But if I do OBP with circuit cutting, you can see the result is slightly even better. And the reason for that is that the circuit depth has been reduced. So effect of noise is less. And I am getting better result at a much, much lesser cost. I can give you a much more dramatic example here for a 19-qubit Hamiltonian simulation circuit. So here, if you see, in general, I would require 3 cuts, but with backpropagation, I can reduce it down to 1 cut. 3 cut would have ended up requiring 1500 circuit executions. But just by doing backpropagation, I can go down to 156, which is almost a 10x reduction. So here also you see that at a 10x reduction, I am getting a much better result. Even my performance is better when I use OBP with circuit cutting. Now let's ask us one small question, something that I didn't talk about. Here I quietly showed that the maximum number of QWC groups. So what is that? When you are backpropagating, you can fix how many non-commuting groups you are willing to allow. That is the quantum resource that you pay for operator backpropagation. Here I have taken that to be 4. Here I have taken that to be 18. How did I find that? So that's a big question. Oh, I forgot this one. So this is something, if you scale it up to 100-qubit Hamiltonian simulation, then the result is drastic, and you can go down from 93,000 close to 94,000 executions required for circuit cutting down to 1,000 executions. This is a 90x reduction. And if you look into the time required for circuit execution today, if you try to do this on a normal IBM quantum computer, it will end up requiring roughly 6.2 minutes. Just by doing OBP plus cutting, you can reduce down to 4 seconds. So either you think around 90x reduction in quantum overhead, or you can think this much reduction in the amount of time. Now, as I was talking about, is that you have this 4 versus 18. So how do you decide? These are not some random numbers, of course. How did I decide 4? How did I decide 18? For that, the first thing we tried, of course, was to try to see if there is any pattern. As we increase the number of max QWC group, can we come up with a nice gradient pattern or something that will help us decide a sweet spot? We ended up seeing that there is none. So this is for the VQE circuit. This is for the Hamiltonian simulation circuit. And if you zoom into here, you can see ups and downs. So there is no apparent structure that we can exploit. We cannot use a general gradient-based methods here. So what we ended up doing is simulated annealing. I'm assuming most of you know simulated annealing. I'm not going to explain it in more detail, but the idea is that if you are going down, if you are getting a better or minima result, you always accept it. if you are getting, if say from this point you are going up here, you accept with some probability. That probability is a function of this capital T, which we call as temperature, and the temperature starts at a high value and slowly reduces. So it's kind of like initially you jump around a lot, there is a lot of entropy, and slowly you settle down. The hope is that we settle down in a very good, ideally global minima, or in a very good local minima. So if I use simulated annealing for different runs, we tried with 5 runs. Here you can see on 6-qubit VQE, I am actually getting that what should be the result. Here for 19-qubit Hamiltonian simulation, it is also giving me the maximum QWC group. And all of these can be actually parallelized if you have an HPC kind of scenario. So it's essentially a single run for your circuit on an HPC kind of scenario, and that gives you the optimal simulated annealing optimal operator backpropagation parameters and the number of circuit executions for that. So just to wrap up, in summary, it uses 2 particular Qiskit add-ons. One is Qiskit add-on OBP, one is Qiskit add-on circuit cutting. So what I showed you results from 2 circuits here, but we tried it for all circuits in bench press, starting from small circuits like 4 qubits, 5 qubits, going up to 64 qubit circuits, large circuits. And in every case, using simulated annealing, we have found that circuit cutting with OPP reduces the number of circuit executions, and 3 to 10x is the minimum scenario where what we are getting. Let's assume that there is an edge case, which is not part of bench press, where circuit cutting with OBP does not help. Like if I do OBP, it will not help. I can think of a circuit, I can immediately prepare a circuit like that, I can definitely think of. But if you do that, if you have a circuit like that, an adversary circuit, if you say, then simulated annealing will return the vanilla cutting as the best case. So where max QWC is 1, it will not allow you to split the terms into split the observable into multiple terms, because that makes the scenario worse. So in one word, if we say, OBP plus cutting has shown better results for every experiment that we have tried. OBP plus cutting has a guarantee that if there are edge cases where this is not useful, simulated annealing will actually reduce it down to general circuit cutting. So we can end with a very strong verdict that if you are doing circuit cutting, it should always be associated with OPP as its preprocessing step, and never anything. There should never be a scenario where using OBP with circuit cutting is not useful, or is at least not as good as general circuit cutting. So yeah, I'll stop with that. And just again telling back that Debarthi did a lot of this work as the summer internship, and this is right now under review at a journal. So thanks for that.
Thank you, Ritajit, for such a very interesting talk. So I think we can take 1 or 2 questions. So please unmute yourself if somebody has question.
Ritojit, before Agar asks me, let me ask something. I could not follow that part when you were mentioning that this is quasi probability. So why it is quasi probability?
So if you actually write down the entire distribution, you can show that it will add up to 1, but not necessarily. Let me just try to share. I mean, I removed quite a few things just to keep it on time. I can just share this one. So yeah, if this is visible, if you see that if I have an RZZ theta gate, I can decompose it into these 6 steps. So these are identity gates, Z gates. This is measurement, projective measurement, and these are the corresponding coefficients. And you can immediately see that these will always add up to 1, but depending on the value of theta, you can have negative values here. So it's a quasi probability distribution, not a probability distribution.
No, so what is important? What is analogous to probability? The square of this or this itself?
No, the analogous to probability is that it adds up to 1. Irrespective of the value of theta, it adds up to 1. But it doesn't retain that between 0 and 1 requirement.
Okay.
So if nobody has any questions, so I think the talk was really very, very clear. So let us thank the speaker and move to the next speaker. So the next speaker is Janani from IBM Quantum Research Lab, and she will be talking about quantum assisted graph optimization with bit string recovery for de novo genome assembly. So Janani, you can share your screen.
Sure. Hi, everyone. Yeah, I'll just share my screen. I think I'll have to exit and rejoin. Unfortunately, it says that the permissions are not enabled for some reason. Sorry about that. Please just give me a minute.
Okay.
Hello, am I audible? Sorry about that.
Yes, yes, you are audible.
Yes.
Please.
I'm just sharing my screen. Sorry about that.
Yeah, your screen is visible. You
Okay.
can go full mode.
Is it visible now?
Yeah, it's visible.
Okay.
Uh,
Is it in presenter mode or like?
no, it's not in the presentation mode.
Okay,
Yeah, you can
full
go
screen,
full
right?
screen. Yeah.
Okay.
Please go full screen.
Okay.
We can see your next slide, Janani.
Okay. All right. I think it should be fine now, right?
Yeah, now it's fine.
Okay, so I'll get started. Sorry for the hiccup in the beginning. Today I'll be talking about quantum assisted graph optimization with bitstring recovery for de novo genome assembly. It's a bit of a mouthful, but this is our recent work which was done in collaboration with IIT Madras. Essentially, we have a quantum solution for de novo genome assembly, which uses like a customized VQE that does a few different things. So yeah, I'll get started. So what is the de novo genome assembly problem to start with? Say we have a chromosome or a piece of DNA from somewhere, and we want to know what are the constituent, what is the sequence of, what is the genome sequence that makes it, makes its unique presentation. As we know, like every program that we write, say classically, is a sequence of bits, right? But each program, depending on the kind of zeros and ones that make it to that make that in the way it is combined, it's a different program. Basically, we have so many different things. Similarly, with organisms, everything is composed of these ATGC constituent molecules, but depending on the sequence, we have different genomes of different organisms. So if we want to go, if we want to read and sequence a chromosome from end to end, it is not a trivial problem to solve even today, despite all the kind of technologies we have. The way we actually find out what the sequence is by performing some next generation DNA sequencing techniques, which help us, which basically make copies of a piece of DNA, and it breaks it down into long and short reads. Now, if we are comparing, if we are going to compare these long and short reads with some existing, genome, and try to find out what, organism it is, then that is something called as resequencing. But suppose we don't want some kind of reference bias, or we are looking at a piece of genome that has high structural variation, say some kind of a cancer genome, or like a polyploid plant type genome, or say if there's some UFO crash or like meteorite crash, and we find some DNA or some kind of genetic material there, then what we would want to do is de novo genome assembly, which constructs genome sequences from overlap, which can be seen in like these short and long reads. In this particular work, what we have done is we have performed end-to-end organism identification via de novo genome assembly. And this is for genome which has been derived from real organisms. And we've done this using both classical and a classical technique to compare and a quantum algorithm, which is VQE. And we basically solve it. So how do we map the genome problem to a quantum computer? So to start with, when you have a piece of DNA, you have to do some kind of classical pre-processing to first get the problem with which you can solve on a quantum computer or map to a quantum computer. It starts by performing some next generation sequencing techniques, from which you basically get something called as a long we basically get some long and short reads, which are then kind of pre-processed in specific ways. You do some kind of adapter trimming. You want to ensure that whatever you use to construct some graphs out of these, they are high quality. That's high quality information that's being propagated. So basically you do some kind of pre-processing, and there are two possible things that can be done. One is called as a de Bruijn graph that can be constructed, and from that you can try to solve via graph. You can try to solve the graph problem from there to find out what would be the sequence. Or you can do something called as OLC, which stands for overlap layout consensus, and you can solve a graph problem. Here the graph problems correspondingly are the Eulerian path problem, where when you basically traverse the graph, you try to visit every edge just once, whereas the like for an OLC approach, you would follow the Hamiltonian path, where you visit every node or like every vertex of the graph exactly once. The Eulerian path problem is actually solvable in polynomial time with order of v plus e, but the Hamiltonian path problem is classically intractable. It is proven to be NP complete. So it makes sense to us that we would want to come up with a quantum approach for the Hamiltonian path problem. Of course, we solve the Eulerian path also, but I think the Hamiltonian path problem has more significance, right? So to give a more maximized view or a more closer look about what this looks like, when you do the short when you basically get these long and short reads, they are going to be bits and pieces of genome that look like this. And when you construct the graph, what you want to do is essentially connect them with edges based on how much overlap exists between these sequences, right? So for example, in this particular sequence, you see a GTG and there is a GTG in common over here as well, right? So then I will assign a weight for this particular edge based on some criteria. So once that is done, you have this kind of a graph. And based on how you formulate the problem, you can either solve a Hamiltonian cycle problem or an Eulerian path problem. So once we kind of do this pre-processing, these were our problem graphs to solve. So we have some 6-node graphs, 11-node graph, 21 and 24-node graphs. All these are derived from some real organisms. So now where do we go from here? Now that we have the problem that we want to solve, now we have to translate this to or encode this on a quantum computer, right? So before I discuss more on the problem itself, this is a landmark paper which I personally really like. It's called Ising Formulations of Many NP Problems by Lucas. And what this paper does is basically give Ising formulations for many NP complete and NP hard problems, several of which are graph problems, right? So essentially what this paper tells us is that there is a way for us to map several NP complete graph based problems to an Ising Hamiltonian. So you have a quadratic unconstrained binary optimization problem, and you can map that to like a problem of solving an Ising Hamiltonian, which means again that you can use an algorithm like variational quantum eigensolver to solve it, right? So essentially that's what enables us to solve optimization problems using VQE. So you might have already come across this, but graph problems like max cut and graph coloring, several of these are solved using VQE for this precise reason. You can come up with a Hamiltonian that corresponds to the optimization constraints of the original Cubo problem. So now let us look at the graph representation. So now that we have this, how do we actually encode the problem, right? So for a very simple, so let us assume that now say we have to find the Hamiltonian path in this particular graph, right? So consider this candidate solution where I have a mapping 0, 1, 2, 5, 3, 4, right? The path looks like this. So I have edges between all these bits and pieces, and I've covered every node exactly once. So now to actually encode this problem on a quantum computer, I need to represent information about the problem onto qubits, right? So there are two main things to consider. So one is the position of, so in this, if you look at this solution, I have the nodes themselves, which are represented by 0, 1, 2, 5, 3, and 4. But there is also the position of each node, right? 0 is in the 0th position, 1, 2, so on. But 5 is in the 5 is in the 4th position, and 3 is in the fifth position, and so on. So I will be using a few qubits to represent the position itself, then a few qubits to represent the nodes. So in a normal Cubo formulation, I will use up first I will convert this representation to binary, and how many digits do I need to represent on a quantum computer. Based on that, I will pick that many number of qubits. So that is the traditional Cubo formulation. But for a hobo formulation, we basically we reduce the number of qubits required. For example, to start with, we fix the position of the nodes. We fix the nodes, and we fix the positions, and the nodes are the only variable. By doing that, we reduce the qubit requirement from order of n squared to order of n log n. So that is the first optimization that we have done. While doing this formulation increases the number of n local terms in your Hamiltonian, it still gives you a much more efficient sort of qubit scaling as you scale up the problem. So for example, when we get to 24 nodes, etc., you use much fewer qubits on on a quantum computer as compared to what you do if you are solving it as a Cubo formulation itself. So before I talk about VQE itself, just to summarize what we've done in this work, we start with classical pre-processing of genome data, which is obtained from real organisms, and the classical pre-processing ends with getting the graph representation as the output. So then we come up with the hobo encoding of the problem and formulate the Hamiltonian correspondingly. The Hamiltonian will contain two main terms. One is the constraint. Basically, what is one of the constraints here would look like, given that it's we are fixing the positions, no two nodes should have the same position, right? So for example, that is a constraint, and that will become one of the terms of the Hamiltonian. The second one is the problem objective, which is to say that when you traverse the graph, when you get a path as the output from the graph, each node should be covered exactly once, right? So you shouldn't have a node repeating in two different places. So that's my problem objective. I will encode that as well into my Hamiltonian. Now we solve this with a custom VQE, which is like a few different things. Starting, we implement this both on the simulator and hardware. On simulator, like what is mainly significant is the fact that we don't use normal expectation computations. We use a CVAR expectation, which stands for conditional value at risk. Essentially, instead of computing expectation values with all the bit string outputs, we only take the tail end of the distribution, which are high quality bit strings that contribute the most to the ideal solution, let's say, in a sense. So then when we come to implementation on real hardware, one of the optimizations that we do is we warm start the VQE, by which I mean that we first solve it on a simulator. We maybe adjust a few different things to try we to like few different hyperparameters during the run, whether it's related to the optimizer or the initial points or like weights of your cost functions. We basically tweak those things a few times, and based on the kind of result that we get from the simulator, we start the VQE warm on the quantum computer by giving the input initial state as the output of the simulator run. So that's the first thing. But aside from this, we also perform M3 readout error mitigation to make sure that readout error is sort of mitigated when we when we perform the experiments. Aside from this, when we actually kept scaling up the problems, we go from 6-node system to 11-node system to so on. At 18 nodes, 21 nodes, we started observing that there were some issues with the results at scale. So what are these issues? I will discuss them in upcoming slides, but to mitigate these issues, or at least one of the main issues, we came up with a novel bit string recovery mechanism, which improves the traverser of the optimizer, again, which is a component of the VQE itself. Essentially, it helps improve the traversal of the optimizer in the solution landscape, which is generated by the ansatz and the cost function. Aside from this, so once we have the results, we also, for having benchmarks against classical, we use dynamic programming to get the solutions for the Hamiltonian path problem. And finally, when we once we solve this and get the OLC path outputs, we use them to generate contigs, and with this we perform organism identification. So now a little bit about VQE and how it actually solves this problem, right? So to start with, we have a graph problem. We have some input. We have nodes, and then the graph has a corresponding adjacency matrix which describes how different nodes are connected, what are the edges, what are the edge weights, and information like that. So to start with, we use an ansatz, just like a normal RX, normal real amplitudes, or we just use the normal two local kind of ansatz, and we use the ansatz and create a general state to start with. This general state essentially represents a general configuration where you have some random path that is described to begin with. Now with subsequent then we calculate the expectation values every iteration, and what is being optimized is the cost, which describes the constraint and also the objective, which is again related to solving the Hamiltonian path problem, which says that you have to visit every node exactly once, and of course other constraints as well. And now, and this is going to repeat until we reach convergence.
Genuinely sorry to disturb you, but since we are running a bit late, so you have 2-3 minutes more.
Yeah, sure. Okay, so yeah, that's what the VQE is going to do. Now okay, so what are the issues that we observed with the results? So at scale, we saw something called as anomalies and violations. Now violations are normal because even in the middle of, say, your optimization routine, you can get a connection which is kind of invalid. So if I have a path which looks like this, but say there is no actual edge between 3 and 5 in the original graph, then this is basically a violation. This can appear even mid optimization. But if I have a configuration like this, where I have a repeated node in the solution, so 2 is appearing twice, or 7, which was not even in the original graph, this is called as a anomaly. So we came up with this bit string recovery mechanism to kind of mitigate these anomalies. Why can they come? First of all, as we scale up the problem, there are several reasons, but mainly you can think of it as so suppose when I create my cost function, I don't put very good weights, or say there are readout errors which don't get mitigated by M3 despite having M3, say they don't get mitigated. So what this bit string recovery mechanism does is it post processes the bit string to find the nearest valid solution. And instead of discarding, say, a wrong bit string, it recovers useful info from it. You can think of it that way. But the main important thing is that it improves the optimizer's ability to traverse, say, the solution landscape and find good assemblies, even especially on like noisy hardware. So so up to what are our results looking like? So with the bit string recovery mechanism, we see convergence at reduced number of iterations. But also more importantly, like say up to say 18, like 9, 11, even at 11 nodes, we didn't see any sort of violations coming up, so we don't really implement the recovery. But at 18, 21, 24, we see some violations. This is on simulator. So we basically implement the recovery mechanism and see that this has reduced the number of violations that come up. And on real hardware, we warm start it and only run it for 50 iterations. But we still see that, we see that like the number of violations which we see in the end, they're comparable with what is seen on the simulators, despite being for only 50 iterations. Now, even with this kind of information, like say we get sequences or paths with a few violations, right? We still kind of try to do organism identification with this kind of output, and we found that despite some reduced query coverage, we were still able to identify organisms at a comparable rate with classical methods. So yeah, to conclude, this is a hybrid quantum classical framework for performing de novo genome assembly that is competitive and scalable compared to purely classical methods. Yeah, this means that for combinatorial bioinformatics problems, we can actually kind of come up with more quantum solutions, especially in this case for a Hamiltonian path problem, which is NP complete and has order of n cross n factorial complexity for classical formulations. We have taken it down from order of n square is usually for quantum, which with respect to QUBO, but for hobo approach, it is only the qubit requirement further reduces to order of n log n. And aside from this, we also do optimizations on the hardware level, like CVAR expectation M3, but also the novel bit string recovery mechanism. So yeah, thank you for your attention. I conclude here.
Thank you, Janani. It was really very interesting talk. So I think we can take 1 or 2 questions. So if anybody has questions.
Ma'am.
Yeah.
Hello, ma'am. I have a question.
Yes.
Okay, so basically, this is your experimental work or theoretical work? First question.
So this is a collaboration with IIT Madras. It is both it is theoretical and also experimental. We mainly the experimental work was done by, say, a few members of the lab. The other more theoretical work was also done by members of the lab, say the quantum, like the part which runs on the quantum computer. But yeah, it's both, I would say, experimental and theoretical in a sense.
Then basically,
Varsha, you can
every node and edges, how you have to represent every data, how you have to do, and how you have to know this data you're correct and your result also correct value.
Yeah. Hi, am I audible?
Yeah,
yes,
you're
yes,
audible.
yes, you can.
Yeah, okay. So we have ways of verifying that, right? So so some of these are like also done by like people from IIT Madras who are like experts in this part of their field, right? So I would say that, yeah, I mean, like we do the organism identification end to end. In my opinion, that serves as a verification in and of itself. But of course, at each and every step, we have ways to verify like whether what we're doing is sensible or not. For example, even for the quantum case, right? We run it on a simulator, then we run it on hardware. We see like the comparisons between the two. So there are like different steps we need to enforce at different stages to make sure that, overall the end-to-end pipeline makes sense. But yeah, that we have ways to do that.
Okay, thank you. So I think let us Misbah,
Okay,
I
ma'am.
think other questions you can email to the speaker.
Okay,
Yeah, Varsha,
okay,
I think
ma'am.
let us take one more question. Varsha, you can
Just
ask your
a
question.
small question, Janani ji. It's a very nice research work. I'm just interested to know that how you are considering higher order in binary optimization.
Meaning like
Kubo.
yeah. So for hobo formulation, basically we map the when we are mapping the Hamiltonian, it is going to like generate more n local terms, but you would find that like while like that more n local terms come up, you reduce the qubit requirement. So one of the ways firstly to do that is to kind of reduce the, I mean, to fix the positions. So by fixing the positions, you automatically remove the need to actually represent it as part of the, say, like qubits itself. So if I say that the first three, whatever comes in the first three qubits, that corresponds to position like 1, then I don't need to add extra qubits to actually represent that, right? So even this, even though it's a cubo, like even though the cubo encoding is sort of standard, or the hobo encoding is standard, there are multiple ways you can do that. So in this case, we have actually fixed the positions and not the nodes. The nodes can move around, which is why you can see 5 appearing in the third position, right, in that sample solution I showed. So alternatively, you could even think about fixing the nodes but moving the positions around, right? So yeah, that like there are different ways to do it, but in this case we have done it by, say, fixing the position and saying that the nodes can be you can have the nodes like flexible in a sense. But as I said, the no, it's not a trade-off exactly, but while you need fewer qubits to encode the problem itself, this will lead to more n local terms in your Hamiltonian. But say the advantage is also in terms of, say, you can have the constrained representation to be more expressive. You will also have, of course, better scaling, right, than Cubo for this specific problem structure. So yeah.
Thank you, ma'am.
So thank you, Janani. So I think let us thank the speaker and move to the last speaker of this session. So last speaker of the session is Faisal Abdul Qadir Khan from Ferguson College, and he will be talking about understanding electronic correlation through fermionic excitations in VQE. So Faisal, please share your
Hello,
screen.
everyone. Yeah.
Faisal,
Please share your
so
screen.
I would
Yeah.
like to take a few seconds before Faisal starts. So
Okay.
that
Okay.
I can see some questions in the chat room, but it's not very clear whom it is addressed. So there are multiple speakers. You all can type questions in the chat room, and because we are less time for discussion, and if I request speakers also to see the chat room and answer. And when you ask a question, means just write at the rate that whom are you asking the question. Like some people have said, can I have a copy of the paper? But it's not clear that which paper you are talking about which talk. So just make use a at the rate, then it will be easier for a speaker also to understand that it is question for him, and he or she can answer in the chat room. So sorry for taking your 30 seconds, and please continue.
It's okay. It's okay. No issues. Is my screen visible?
Yes, but it's not in full screen.
Yeah.
Now it is full screen. Please
Yeah,
continue.
fine,
Now
fine.
it's full screen. Yeah. So, my name is Faisal Khan. I'm from Ferguson College, and today I will be presenting my work title, Interpreting Variational Parameters in Excitation-Based Quantum Algorithms. So, variational quantum algorithms are currently among the most promising approaches for performing quantum chemistry calculations on near-term quantum computers. However, one important question that comes into mind is, what do these variational parameters actually mean? So, my work is based on that, is to be able to actually interpret what these variational parameters mean physically. So, in this work, we investigate the physical meaning of this variational parameters by studying fermionic excitations, operators in the UCCSD ansatz, and analyzing how strongly they influence the ground state energy. The problem statement that we have taken is, as I mentioned before, we are going to take a linear H4 chain and we are going to perform VQE on it, and then we are going to perform a perturbation on the variational parameters to be able to analyze which parameters actually have the strongest effect on the ground state energy that we have calculated. So now a little bit about variational quantum eigensolver before we begin. It works on the variational principle where the energy calculated is always going to be greater than the true ground state energy of the system. And now there are four main components of a VQE calculation for our purposes. First is the Hamiltonian, which is going to encode all the information about the energy of a molecular system. And now our goal is to find the eigenvalue of the minimum eigenvector of this Hamiltonian. For this purposes, we are going to build an ansatz. It is just a quantum circuit which has parameterized, which is essentially a parameterized trial wave function, and it is going to help us in approximating the eigenvector that we are seeking. And then we have an estimator, which is a means of estimating the expectation values of the Hamiltonian H over the current variational quantum state. And all of this is wrapped around a classical optimizer. I'm sure all of you are familiar with Corbilla and SPSA and all the others. Now, let us discuss one of the components of VQE, the Hamiltonian. First of all, a Hamiltonian of a system can generally be split into two parts, as we see here. The kinetic energy or the momentum T and the potential energy V. Now, these themselves have various components in them. For example, in the potential energy, it can be divided into three parts: electron, electrons, nucleus, nuclei, and the electrons and nuclei terms. Similarly, we can do the same for the potential, for the kinetic energy T. This is split into two parts furthermore. Now, to reduce this is a huge Hamiltonian problem, and to do this exactly on a quantum computer would require an exponential amount of resources. So to do this, we use the Born-Oppenheimer approximation. And using that, we essentially fix the nucleus as stationary as compared to the electrons that are there. And this is the equation that we come up with for the Hamiltonian. Now the question is, how do we translate this Hamiltonian into fermionic terms, fermionic operator terms, which we later translate into Pauli terms. So to do this, we use fermionic operators, which are known as creation and annihilation operators, which we see here. And once we actually go through this, a huge number of I know equations are there, but essentially the result that we get is this shortened fermionic Hamiltonian. After that, we move on to a mapping. For mapping, we use the Jordan-Wigner mapping for simplicity. It is the most simple kind of mapping that we can use. There are many more, such as the Breivik-Kitaev and many others. So with this, we translate the fermionic operators into Pauli terms. This Pauli terms meaning the Pauli matrices that we see in quantum computing. The Z Pauli matrices and the X and the Y. So an example of this Hamiltonian, of the mapped Hamiltonian to the Pauli terms, is seen here for the simple H2 molecule. Now, what we are working with is an excitation based ansatz. It is known as UCCSG, essentially known as unitary coupled clusters, singles and doubles ansatz. So what this does is it encodes the fermionic excitations as Pauli terms. And for this, we start with the reference state, the Hartree-Fock state, and then we use the fermionic excitations as seen here. These are single excitations where an electron is moving from an orbital I to a virtual orbital, occupied orbital I to
So Faisal has apparently stopped. Means is it my problem or it's stopped for you all?
Yeah, it stopped for all of us, I think.
Yes.
So just a moment, let's wait probably, and he will rejoining. Or Faisal, can you hear us? Means I still can see him in the meeting room. Shandip, if you have his
Basil?
number.
Basil?
You are not audible, means I can see you log in, but Shandip, if you have his number, just call in the phone number. There may be an internet issue.
I think there will be signal issue.
He's not responding.
So when was the next talk in proper as per
7:40. We have 5 minutes.
we are almost there at
Yeah,
7:35. So
yeah.
we can take the minutes. We can discuss, and if someone has any question for the previous speakers, you can ask before we move to the next session. Or in general, any comment, we can take 2-3 comments or questions before we move to the next session.
Hi, Jenny. I have a question from Jenny, I think.
So, Janani, are you here?
I think she is not here.
No, Janani has left the room.
Okay, fine.
But if you have any, question is difficult to address in her absence. But if you have any remark, you can make that.
Sir, it was just a question to ask that there were some further activities or possibilities if she has performed that.
Okay.
Sir, what is the question? Pardon?
The question is, you are the part of the work?
No, I just want to know the question, sir.
Oh, okay. So the question was, since she has used the Ising-based encoding, but now in some particular cases with some particular constraint, even the Heisenberg kind of spin chains can be used for relatively efficient encoding. So has she tried in that direction? Because I understand that would be much more resource intensive, but still with some constraint or etc. In some particular cases, that is much more efficient than Python. That's what I wanted to ask.
Okay, sir. Thank you.
She has tried.
Anything else from anyone? Any remark or any? So if not, we slowly move towards the next session. And is Dr. Shibanishing around?
Yes, sir, I'm here.
Okay. So before we move to the next session, I would like to thank Dr. Shandip Misra for chairing the previous session. And as it's a young scientist meet, so I mean, there are two old men in the beginning, means Professor Mani and I spoke, but otherwise all the sessions will also be chaired by the young quantum scientist. And the next representative who will chair the next session is Dr. Shibani Singh, who is also our colleague at JP Institute of Information Technology. But before that, she did a PhD from Mat Science or IMSC Chennai. Subsequently, she was a postdoctoral fellow for a pretty long time at Prague. And she works on many aspects of quantum optics and random number generation, quantum random number generation. So quantum walk, etc. So because this last session, we have seen that we are not getting time for asking question. And finally, we got some time because of internet glitch, but let's move on. And the stage is over to Shibani for conducting the rest of the day's session. Means we have only 2 sessions in a day. So it's starting of the second session and over to Dr. Singh.
Thank you, sir, for the introduction. So welcome everyone to the second session of the quantum computing. So the first talk of the second session is by Dr. Abhishek Sadhu from University of Birmingham. He's going to talk about the aspects of variational quantum algorithms. So let's welcome Dr. Sadhu.
Hi. So let me just share my screen. Okay. Yeah. Can you see my screen?
No, we can't see you.
Can you see my screen
Yeah,
now?
yeah, yeah. Now we can see your screen.
Now we can see, but it's not in full screen. Make it full screen.
Yeah, I will do that. Yeah. Okay. Just give me a minute. I will do that. Yeah. Is it like it is full screen now, right?
Yes, it is.
Okay. Hi, everyone. So thank you. So firstly, thank you for giving me the opportunity to present our work. So today I will be talking on different aspects of variational quantum algorithms. So the objective over here is to automate the optimization of quantum circuits for different tasks of interest. And so our work can be broadly categorized into three different aspects. So the first one, which we call CART-CUS. So it essentially involves solving or designing quantum circuits that can be distributed among different quantum processors. So the second one is called CANCUS, which essentially involves um, designing a novel quantum algorithm or a novel uh, RL framework, reinforcement learning based framework that can be used for creating or designing quantum circuit that can solve different tasks. And the third part of the presentation, which is KIT-CAS, which is essentially where we try to understand the different where we try to understand why the quantum circuit is essentially producing the why we are essentially getting the quantum circuits for this task from the RL agent. So the general framework is as follows. So there is a reinforcement learning agent over here who starts with a blank circuit and has an action space available to it, which consists of different gates that he can apply to the circuit, and then he applies a optimization routine to solve the task of interest. And he essentially and his marker is essentially a reward function which he tries to maximize. And at the end, we will be getting a quantum circuit which essentially solves our purpose. Okay, so just an overview. So there are basically three different components of variational quantum algorithms. So firstly, there is a quantum processor which prepares a quantum state, and then there is a classical computer which takes a quantum state and evaluates a loss function or a reward, and then there is an optimization loop in there's an optimization loop which essentially takes the reward function and plugs in the quantum gate of interest, which will help us in solving the problem. So yeah. So now so this field is essentially called quantum architecture search. So as you can see over here, so we start with a blank circuit, and then there is a search algorithm which essentially plugs in the different gates that will help us solve the problem based on the reward function, which can be calculated from a classical computer. So so the first question that we should ask is why we are using reinforcement learning. So reinforcement learning offers certain advantages because we firstly do not need any prior knowledge of architecture, and also it has the potential to come up with innovative solutions, and also the adaptability towards training towards correcting errors during the training process. But now we can only do this if we have and if we can efficiently encode the RL state and also properly engineer the reward function. So the first part, so over here we essentially design a novel framework, a reinforcement learning framework that essentially combines or takes into consideration the hardware topologies of different quantum processors in the reinforcement learning framework to come up with optimal circuits that can solve our problem. So with this, what we do over here is essentially we try to solve for the ground state of different molecules. So we had over here considered the 4-qubit hydrogen molecule, the 6-qubit lithium hydride molecule, and also the 6-qubit beryllium hydride molecule. And we have considered the effect of different topologies. For instance, if we look at the 4-qubit molecular case, so we see that the linear topology and the triangular topology can give us the optimal circuits with the minimum depth and minimum C naught count as compared to other topologies for as compared to other topologies such as square and T topologies. But also note here that we actually
are in the limit of chemical accuracy for all these tasks. And so now if we say take the four qubits and then say try to divide it into two processors, say the we find that the most optimal way of doing it would be to have one isolated qubit and one qubit and 3 qubit in another processor in a linear fashion. So with this we can, as you can see, we can achieve chemical accuracy, and so and we have optimal c0 counts and optimal depth. So essentially what we see over here is that the 3 qubit quantum processor can effectively solve the 4 qubit hydrogen problem. Okay, and so now we also see for other different molecules. Say if you look at the beryllium hydride molecule, we see that we can divide the 6 qubits into two 3 qubit blocks and put it on different quantum processors, and then we can actually reach chemical accuracy with feasible number of gate counts as well as depth. So now since we are moving towards a NISQ era where the qubits are noisy, so it might be preferential to distribute the algorithm into different processors and try to solve our problem. So maybe if you have any questions, maybe you can interrupt me, I can take and then move forward. Okay, so now for the next part, so so if we look at the reinforcement learning based approach for solving this kind of optimization problem, so one of the major steps is the function approximator stage where the agent essentially tries to find a gate that it essentially applies to the circuit next. So in traditional RL algorithms, it is based mostly on multi-layer perceptron models, but we essentially move away from that, and over here we introduced a Kolmogorov-Arnold network based model. So the difference over here is that in a multi-layer perceptron model, the training is over the space is over the ages and weights, but in a Kolmogorov-Arnold network based model, the training is over the activation function space. So that actually adds to the interpretability of the model, and we wanted to see whether we can get some advantage with this or not. So for the first task that we consider for this is the quantum state preparation problem. So for this we essentially take the 2 qubit well state preparation and a 3 qubit GSE state preparation, and we essentially see that there is a clear advantage in using CANs over multi-layer perceptron in the RL framework. So as you can see over here, so in this graphs, the probability of success essentially denotes the number of the number of successful circuits that you get over the total number of circuits that the RL agent generates. Or so you can see over here that there is a clear distinguish. Like for instance, if we allow the whole algorithm to run, then there is the CAN based algorithm can essentially reach success probability which is very close to zero 0.5, but while the multi-layer perceptron can reach at most around point something close to zero 0.4. So the first question is, does CAN have a better success rate than multi-layer perceptron with increasing time? The answer is yes. So the second question that we ask is, does CAN utilize lesser number of trainable parameters than multi-layer perceptron? Same answer. Here also we see that there is a clear advantage. So if you consider the task of Bell state preparation and JZ state preparation, so CAN can actually can essentially solves the problem requiring around 1728 number of parameters for the noiseless Bell state, where multi-layer perceptron essentially requires 4782, which is slight which is way more than we require for CANs. So now if you're constrained with the number of trainable parameters that you can use in your framework, so we see that CAN is the way to go. The third thing is that is CAN better compared to multi-layer perceptron in optimizing the structure of parameterized quantum circuits? It depends. So as you can see, when we try to solve the hydrogen problem, then if we look at the depth of the circuits, then CAN and multi-layer perceptron provide comparable depth, but there's a slight advantage in the 2 qubit gate count. And if you see the total number of gates that you require to solve the problem, then CAN is slightly a disadvantage. While if you try to solve the lithium hydride molecule, then you see that in terms of the 2 qubit gate also, and in terms of the depth also, CAN has an advantage. while multi-layer perceptron does slightly better when you look at the total number of gates that you require for solving the problem. So like if you, so in a nutshell, if you ask that is scan better than multi-layer perceptron in optimizing circuits, it depends on what you're trying to do. Okay, so now the final thing that we ask for any algorithm is about the runtime. So we ask essentially that is scan faster than multi-layer perceptron? The answer is no. So as you can see over here, that for the same problem, can, like for instance, if you look at the GAZ state preparation problem as well as the hydrogen ground state ground state solution problem, then can requires around, or can requires time which is orders of magnitude more than you would require for multi-layer perceptron models. So can is way slower than multi-layer perceptron in terms of the training time. So to summarize, does can have a better success rate than multi-layer perceptron with increasing time? The answer is yes. Does can utilize lesser number of trainable parameters? The answer is yes. Is can better than multi-layer perceptron in optimizing the structure of parameterized quantum circuit? Then it will depend on the task that you are trying to do. And finally, is can faster than multi-layer perceptron? The answer is no. Okay, so with this, I will move to the last part. So over here, we try to understand why the RL agent is essentially producing the circuit that the RL agent is producing. So for this, we take the task of quantum state diagonalization. So and we take the routine from the work by Danko Vedran and others. So essentially, we start with a blank circuit, and then the agent starts with a blank circuit. And iteratively it uses a deep neural network model to predict the next gate depending on the reward function and the state of the answer that it currently has. So and tries to solve the problem. Okay. So firstly we see the we to analyze the circuits the RL agent is generating, we first see its entanglement generating capacity. So we vary the concurrence of the initial state and get the circuits, and essentially the RL agent gives us a plethora of circuits, and from this plethora of circuits we observe the entanglement generation capability of the circuits in terms of the lower bound and upper bound. And so to do this, what we do essentially is we take the circuit, we plug it, we plug into the circuit a separable state and see the state that we are getting and observe the concurrence of the state. So that is how we see the lower bound and upper bound of the circuits, and we see that beyond till a certain point, that is till the concurrence is around 0.3ish, there is, so this both of these are anti-correlated. And yeah, so like there is a phase transition point at around zero point 0.3. So if we look at the PCC, cumulative PCC from the starting point till around zero point 0.3, so both of these are negative, and after zero point 0.3 the PCC becomes positive for the upper bound, while it is still negative for the lower bound, showing that these two act in opposite natures. Okay, so now with this observation, we essentially add a entanglement enhancing block before the RL agents or before the unsurge, and with this we see a drastic increase in the performance of the circuit. So we observe that the total reward that the RL agent has collected, as well as the total number of successful episodes the RL agent could find, has more than doubled with this entanglement enhancement. And also we see that there is also a reduction in the 2-qubit gate count. So we thus see that adding an entangling block before the unsurge essentially helps or improves the performance of the RL agent. Okay, so and then we wanted to see what the contribution of each of the qubits to the for the algorithm. And so for this we quantified via the difference in the conditional entropy. And for this we see that there is no preferential uh, qubit, which are both the qubits contribute equally to the RLVQSD unsurge for the change in entanglement. So so to conclude, so we move towards a path. So we move towards a unified physically grounded framework that combines the parameter efficiency of Kolmogorov-Arnold network with the depth of quantum information theory to create a transparent and robust quantum architecture search method. And so we go beyond the black box optimization by linking performance agents to physical phenomena like phase estimation and interqubit correlations. And so, and also for future duration, it might be interesting to embed some of the metrics such as entanglement measures and hardware connectivity into the reward function that says that it can steer the RL agent. And we can also incorporate the circuit cutting methods to scale to further scale and enhance the explainability of cons, and also scale concus beyond toy models. So this is our team, and thank you. If you have any questions, I can take.
Participants can unmute if they want to ask any question.
So basically, sir, I have some question.
Yeah.
So basically, you have to use this molecule, means LIH and H2, or any molecule you have to use H2 support. Then basically, coefficient, how you have to find? You know, coefficient, what is coefficient, and how you have to represent this every coefficient and everything.
No, sorry, like if I understand correctly your question, like what coefficient are you talking about?
Coefficient means, suppose you have to optimize this molecule, mean LIH, okay?
Yeah.
Then there have also you have to put Python code. Then there have also need coefficient. If you do in your work, or any present, you have to present any paper. If you do this work yourself, or you have to present this.
No, like I did it with my collaborators Akash and Orithro. So we did. So essentially what we did is that, so we firstly take the molecule and then we do something like a Jordan-Wigner or a parity-based mapping and convert it into, and then
And basically, what you have to use, basis set,
Sto3G, we use
basis.
Sto3G.
Okay, STO3G.
Yeah, we use Sto3G basis set, yeah.
Then there have also coefficient. Then my question is, coefficient, how you have to find that? This is my question. Means the difference molecule, difference coefficient, and everything is like that.
Yeah,
Okay.
so essentially you write the whole, like as the previous speaker was saying. Yeah,
Coefficient.
So,
Okay.
so for instance, you take a molecule. So you take a hydrogen molecule and you say that your interatomic distance is something, and then you can write your whole Hamiltonian in terms of your fermionic operators, right? So once you have that if once you have that fermionic operators, then you can essentially do some sort of a mapping and convert it into your qubit Hamiltonian, right? So now once you have your qubit Hamiltonian, you can feed that into your RL agent. So the RL agent essentially starts with a template circuit, which is a blank circuit, and then depending on and you define your reward function, which is essentially your expectation or your minimum energy that you're trying to solve over here. Okay, so then what the RL agent starts with a blank template circuit, and then depending on the cost, it just plugs in the optimal gate that would be suitable to minimize the.
Okay. Your voice is not clear. I think maybe your internet is working.
Okay, so what I'm trying to say is that, so you have your, so like after you have your second quantized Hamiltonian, and then you place your Jordan-Wigner mapping or some sort of mapping that you take to your qubit Hamiltonian, right? So and you plug that Hamiltonian into your RL agent. Okay, so what the RL agent does is that it has a set of gates that is available to him, and then depending, and you define a cost function, which is essentially the expectation value of your Hamiltonian, right? So now the RL agent starts with a blank circuit. Then it just plugs in the gate one by one, such that the energy is decreasing, and then so essentially what you are essentially doing over here, you are essentially solving something called a Bellman equation. Okay. So like there is something called a Q value equation which you are
Can I show something?
trying to solve. Yeah.
Can I show this? You have to see that there have also used 0, 0, 0, 0, 0, 1.6, and also they are also showing minus 7.4. This value, how you have to find? My question is this: 1.6, this value.
Misbah, I think those kind of things can be discussed later on. Yeah.
Okay, sir. Okay, next time. Okay, I have to message you. Okay,
Yeah,
okay.
no
Thank
worries.
you.
You can share the screenshot and write in chat room, and you can talk. You can continue this discussion in a chat room, in the separate chat room, and we can move to the next talk. So, Dr. Shivani, please.
I have a question, sir.
Okay. Just
Just one
quick,
for a
be
second.
quick.
I will not take much time. Abhishek, just a quick comment I was expecting from you. So, do you have any, could you find some constraint or some kind of preferential conditions while for under which it can read more efficiently, the RL, reinforcement learning can read more efficiently, so that like for the what kind of structural it is more it favorable to? Is there some any insight while dealing with, because you have dealt with multiple molecules, that's why I said.
Yeah, so thanks for the question. So it actually depends on the task that you are trying to do. Okay, so like for instance, if you are doing the diagonalization problem, then if you just add an entangling block just before the answers, that helps. Okay, so now so to do, okay, so another way of answering your question would be, so like there is something called a gadget reinforcement learning which people are doing these days. So you start with a vanilla reinforcement, so you start with something called a vanilla reinforcement learning, which is just a plain guesswork. So you let the agent train, okay, and you get the circuits, and then you see for patterns in the circuit, okay, and then you use those patterns as custom gates with the previously used gate sets that you had, and then you iteratively train, and that might actually help in improving the performance of your agent.
Okay, my question was a little bit quite related, but just as a comment, I will not expect the follow-up. But so many times, even in these cases, many times this biasness is still there, and that is still a problem when you start going towards the relatively larger molecules. So this kind of biasness, to overcome this kind of biasness, some structural conditions might be favorable, might not be favorable. So my question was posed at that place. So that was the reference.
I see. Okay.
Anyway, we can discuss it later. If
Yeah, sure. We can catch up. Yeah. Thanks for the question. Yeah, it was nice. Yeah.
Let's thank the speaker. Thank you, Dr. Sadhu.
Thank you so much.
Thank you for your talk. And let's invite the next speaker of this session, Dr. Santoshi Kumari from Chaitanya Bharati Institute of Technology. She's going to talk on hybrid quantum neural networks for medical image classification. So let's welcome Dr. Santoshi. Hello. Dr. Santoshi Kumari, if you're there. I think
Dr. Santoshi, I think she is present in the room. Yeah. Dr. Santoshi?
either there could be a network issue or
This may be a glitch. Let's check. Dr. Santoshi is in the room.
there could be a network issue.
I can see her. Who is the next speaker?
Yeah, I think we can call the next speaker and reschedule the talk of Santoshi in the other.
So the next speaker is Dr. Akora Murthy B from National Institute of Technology, Pondicherry. He's going to talk on noise-aware quantum error mitigation. So, Akora Murthy B, if you are available, can you please share
He's
the
there and he's
slides?
sharing his screen.
Yeah.
So good evening. Am I audible? And I think I'm
Yes,
visible.
perfectly audible.
Yeah, thank you. Thank you. One sec. Let me. Yeah. So very good evening. I think my screen is in full screen.
In the meantime, Dr. Sandeep, you can try to get in touch with Dr. Santosh if your phone means if there is an issue, let us know.
Yeah. Sure. Um, shall I start?
Yes, please start and continue.
Yeah. Thank you, everyone. Thanks for the opportunity. I'm Akoda Murthy from National Institute of Technology, Puducherry. I'm a research scholar, senior research scholar, and doing my research under the guidance of Dr. B. Surendran. And today I'll be talking about noise-aware quantum error mitigation via physics-embedded liquid neural networks. So this work was carried out within QAM framework, which is CRISPR Advocate Mentorship Program, and under me there were five different mentees from all different parts of the world, and we were able to successfully exhibit this project some 2 months back, 2 months before in open house of cricket advocate mentorship program, and it was approved also. And today I'll be talking about it, and very sooner it will be published in a it was submitted to one QN journal, and we expect very sooner the result. And so moving over, yeah. So at its core, as you can see from the slide, Palin sits at the intersection of three ideas. You can see on the slide, right from disk era computing, liquid neural network, and physics constrained machine learning. So the fundamental question here we are trying to answer is that given the quantum hardware is inherently noisy, and given that full quantum error correction is still beyond reach, so can we build a learning system that is smart enough to correct those errors dynamically, efficiently, and physically consistent? So the project is a solution for that question. So this framework we have done is evaluated on a random quantum circuit ranging from 4 to 9 qubits, and it is benchmarked against two most widely used error mitigation methods, which is zero noise extrapolation and Clifford data regression. So moving over, let me talk about the motivation. And this is a story that most of you in this session might have known, but let me quickly wrap it up. So we are in the NISQ era, right? And which is noisy intermediate scale quantum devices, and these devices are powerful enough to be interesting, but noisy enough to be unreliable, isn't it? And also they suffer from gate errors, decoherence, and readout errors, readout noise, etc., etc., all of which corrupt the measurement result we care about, isn't it? And now the textbook answer for this question is always we know, and which is a quantum error mitigation. That is a classical post processing that tries to estimate what the ideal noiseless answer would have been, isn't it? And this is much more tractable problem for a near-term hardware also. But here is a catch, and this is a key motivation for our work where noise is not a static. And like you can see from the third box here, which is T1, T2 gate fidelities, and they all drift between the calibration cycles and across different qubits. Uh, also, we came out with a method which learns to correct one noise profile, will miscalibrate when the hardware drifts from one to another. So this is exactly the gap Appealin is designed to fill, and we wanted a mitigation method that adapts dynamically to the current noise environment without requiring frequent retraining and without making any unphysical prediction also. So moving over. So let me describe the Palin architecture here. The model has three sequential components here. First, the input encoder, as you can see from the slide. Given, let me give an example. Given a vector of noisy observable measurement, let's say, we assume the three Pauli expectation values from the quantum device, and the two layer MLP maps to those into the 64 dimensional internal representation. So what it does is this particular part will be doing the future extraction step actually. And moving over to the second one, which is most important one, which is an LTZ block here. We stack two liquid time constant neuron layers on the top of the encoder. And the key property of this LTZ neuron is that they operate in a continuous time, and their hidden state usually evolves according to the ODE, and I'll say more about the mathematics on the next slide. and crucially, their effective time constant adapts dynamically to the input here. And this is what our model, what we propose is adaptive, and it's going to be time varying behavior also. And talking about the third one, which is here, I think pointer is moving. Yeah. Talking about the third one, physics decoder, it's a linear readout layer that produces a pre-activation value, and which will be then passed through a tanh projection, which is scaled by the observable operator norm actually. And so this particular block will ensure that all the mitigation predictions lies within the physically valid range. Actually, it is a hard mathematical guarantee. And so now look at the bottom of the slide. The entire model has approximately 18,000 trainable parameters, which is having an orders of magnitude smaller than typical sequence model, of course. And inference requires only a single circuit run, where you can see, and which is compared to k runs of ZNE, and per sample cost is actually O of D square. The inference block we took is only O of D square, floating point operation, and it is deliberately a lightweight architecture designed to design deployed practically on a real NISC hardware. So moving over. Let me get into the mathematical core of it, as I already told you. So I want to highlight two important results that I think we are particularly, that the result is more elegant when compared to other things. So the first is liquid time constant ODE. Here, each LTC neuron evolves according to the equation given, according to this equation, and dx by dt is equals negative 1 over tau plus f of theta, which is multiplied by x plus f theta of times. So here what matters is the effective system time constant tau is shown in this equation. Okay, what happens here is the time constant is input dependent, and when f theta is large, which meaning that the neuron is processing strongly a noisy input. And when tau strings, this particular thing strings, what happens is that the neuron responds quickly. When the noise is low, the tau system expands, and the neuron averages more smoothly here. So this is a key adaptive mechanism, and the network dynamically adapts to temporal sensitivity in order to match the current noise region. So the second result is a physics embedding here, and this one I want to emphasize much more harder than the previous one. Like for any Pauli observable, quantum mechanics will be dictating the expectation value should be between -1 to +1, isn't it? And this is the operator norm bound, and we enforce this as a hard constraint in our work through the tanh projection at the output layer. So, though this theorem, this gives us a theorem one actually, which is called physics consistency, which you can see in the box at the bottom. Let me read it. For any parameter theta and any input x, the absolute value of the model output g theta of x is always at the most, always at most the operator norm of O at. And the proof is actually trivial but important. Tan H is bounded strictly between -1 to +1. So the product is always lesser than the norm, which is OED. And this is not a soft regularization, actually, I should say, and it is a provable guarantee. And no matter what the noise model sees, the prediction will always be a physically valid. That is something the baselines like DNE or DDR cannot claim. Okay, and moving over to pipeline. So talking about the first box, we generate a random quantum circuit, specifically random Pauli rotation layers, which is interleaved with C naught entanglement layer. For a qubit counts ranging from 4 to 9 here, we consider, and we generate nearly 5,000 training circuits and hold out 1,000 for the testing. And talking about the second box here, for each circuit that was created in the first step, we simulate both the noisy version and then ideal noiseless version using the Qiskit AER. And the four noise models we test are depolarizing, amplitude damping, and thermal relaxation and readout error, which actually covers the main physical channels seen in real superconducting hardware. And talking about the step three, which is a data set construction, we assemble a data set of paired, noisy, and ideal observable expectation values. So, and also we vary noise parameters by plus or minus 20%. So, across all the training circuits which were created, and to ensure the model is exposed to a range of calibration conditions. And talking about the first step, which is the Palin training, we have done the training using the atom optimization with the cosine annealing learning rate schedule over 500 epochs. And talking about the fifth step, the models evaluated and benchmark against the famous ZNE and ZDR across all the qubit and in a cross-night settings also. This is where we actually turn now. And talking about the noise model, so let me have a quick word on the experimental setup for the completeness. The four noise model tested are depolarizing noise with single qubit error at 1% and the 2 qubit rate at 2%. Amplitude damping with T and T1 of 50 microsecond and thermal relaxation with both T1 and T2 TK and readout error with a 35% state confusion probability here. And these parameters actually or the representation of current IBM quantum hardware. And these two baselines, talking about these two baselines, ZNE and ZDR, are ZNE using, we have done using the Richardson extrapolation with scale factors 1, 2, and 3, and CDR, which is Clifford data regression, trained on 500 near Clifford circuits per test circuit family, actually. So critically, we introduced the cross-noise evaluation protocol also here, which you can see here. And rather than testing under the same noise model using the different used during the training, what we did is we trained on different noise type and tested on completely different unseen noise type. So I can say that this is the most realistic experimental condition, and it is where the adaptive properties of the Palin really matters. So our evaluation metrics are like MAE, which is mean absolute error, RMSE, root mean square error, and maximum absolute error, which is reported across all the qubit counts here. And moving over, so let's look at the result. These two charts show mean absolute error and RMSE as a function of qubit count for all the for all the three methods here. The first thing to be noticed here is the red line, like as you can see the red line here, which is the ZNE. It degrades drastically as the qubit count increases, isn't it? Also, with RMSE reaching its 4.26 at the qubit number 7 here. So this is exactly what we expect theoretically as the circuit depth grows. The noise amplification factors in the ZNE creates a circuit that are far outside the original noise region. So, which makes the polynomial extrapolation numerically ill-conditioned. Okay, and talking about the blue curve, which is our proposed system, and the green curve is the CDR. Both behave much more stably actually. I can see, you can see here at the qubit number 4, at qubit number 4, the PLN achieves the lowest ME of 0.031, which outperforms both CDR and ZNE by about 8% nearly. And at the 5 qubit, let me be more transparent here. CDR significantly outperform PLN, but we believe this is because CDR's near Clifford training circuit happens to cover observable distribution at the scale particularly well, actually. So while randomly, sample training circuits are sparser in this relevant region. So this is something we are actively working on to address the future to address as the future work through more structured circuit sampling here. And talking about the qubit 6 onwards, PLIN, like our proposed system in CDR, becomes essentially indistinguishable in MAE, but while ZNE continues to degrade here. And talking about 9 qubit, PLIN matches CDR exactly both at having the MAE of 0.059 and while ZNE is at 0.1, more twice the error actually. Okay, so moving over. Now, here is the most striking findings in our experiment, as you can see, and I think it really motivates the need for physically constrained model also. And look at the Z maximum here, Z maximum absolute error at 6 qubit. What happens here is the value is actually crossing the 1, isn't it? Which is actually 1.028. For anyone who works well with the Pali observables, they know that the number should be immediately, they'll be raising the red flag here because the physical operator norm bound for a Pauli observable is exactly 1.1, and ZNE has produced a prediction that is physically impossible. So that is a problem. That's a problem here. And this is not numerically artifact. It is a fundamental consequence of unconstrained polynomial extrapolation. So when you push noise amplification too far, what happens there is the extrapolation value will land outside the physically valid region here. So with help of our theorem one, what I discussed in the previous slide, the peel-in, will not be doing this kind of physically unlawful thing. So the tangent projection is a hard barrier actually what we have used, and no matter how noisy the input, no matter how extreme the noise region, our prediction always stays within one to plus one to minus one for any poly observers. So the right hand panel, as you can see from the right hand side, which shows the relative MAE gains over peel-in over ZNE actually. For n greater than or equal to 6, we consistently see the gains of 40 to 60% here actually. And so this is the full complete results table across the 3 representative qubit count. We can show right from 4, 6, and 9 with the best performing method per highlighted here. And let me give you directly. Let me talk about it directly. The key message here is peel-in is never the worst method, and it is the best or the joint best method in the majority of the cells in this table, as you can see. And while additionally it proves the physics consistency guarantee when compared with the benchmark, which is CDR and ZNE. So this is what the values I was talking about in the previous slide. And and these two plots gives a wider view of the performance landscape here. And the radar charts on the left compared all the 3 metrics simultaneously at 4 and 9 qubits. And with 4 qubits, peel-in enclosed area is the smallest. You can see peel-in's area is very smallest. It tells the story like it is very closest to the zero error across all the 3 dimensions. And at 9 qubits, peel-in and CDR are essentially superimposed. You can see here. And the heat map on the right hand side, sorry, the heat map on the right hand side shows the full MA matrix, and the green cells are lower error and red cells here are higher, and the pattern is very clear, right? The GNE's row gets progressively redder from left to right, and while PNE and CDR remains relatively stable. So there is a local maximum at 5 qubit and 5 qubit to 6 qubit here, and for the learning based method, then both became plateau from 7 qubit onwards, isn't it? So you can see from here. So now, and this slide shows what I'm showing here is I consider the most practically important result in this paper, which is cross noise generalization, where in a real deployment scenario, the noise model of devices experiencing at inference time will not be exactly the same as what you have trained on, isn't it? So mostly this is what we experience. So devices usually drift, and the calibration also changes. So we deliberately train one noise model, and what we did was we evaluate on a different noise which is completely unseen. Okay, so the bar chart here, for such trained search pairs or has been depicted here, where PLN achieves the lowest cross noise MAE in 3 of the 4 pairs. And in the fourth pair, there's CDR, and you can see CDR edges ahead where PLN is still competitive in comparably. So why does CDR degrade more sharply in some settings? Of course, there you might have a question. I can answer it here itself because CDR's near Clifford training circuit implicitly encode assumptions about the current noise channel. So that is where the problem. And when the channel changes, the encoding is no longer accurate, and the regression model transfers poorly actually. So that is why CDR degrade more sharply actually. And so getting into the slide again, PLIN's LTZ hidden state by contrast can adjust its temporal dynamics continuously in response to the changing input pattern. So it partially compensates for the distribution shift even without explicit retraining. So this is the adaptive advantage of using this continuous time learning. So as you can see, see the quote at the bottom, the PLIN demonstrate robustness that existing system lacks. Okay. So talking about, I'm going to talk, let me quickly walk through the 3 different columns here I've given here. First one is what we are proud of and what we are honest about. Second one, and third one is where we are heading. So they're talking about the what we are proud of. and we add, like our model adapted to LTC dynamics without retraining, and also the physics safety guarantee from the theorem one, what we have discussed, and single shot efficiency at one circuit overhead, and scalability that matches CDR at 8 and 9 qubits. And talking about limitation, of course, I should accept it. I want to be more upfront about this because all of the results are from Qiskit AES simulation, and hardware validation on IBM Quantum or similar devices is the critical next step, and we are actively pursuing that also. Also, we also evaluate scalar possible poly observables, and we are planning to extend that to which will lead to architecture modification also. And talking about the future work, we are currently implementing a continuous LTC update rule for real-time noise tracking, and hardware experiments on IBM Quantum also we are moving over, and integrating PLN as a mitigation background for VQE and QA/OA workloads, and the transfer learning, also pre-training on simulation, then fine-tuning on small set of real hardware measurements also. So these all are some of our future works we are planning on. So moving over to the conclusion. So PLN, the proposed model, couples continuous time LTC dynamics with hard quantum mechanical constraints, which produces novel error mitigation framework. And talking about theorem, it provides a provable physics consistency guarantee, something that other baselines like ZNE or ZDR will not offer. And talking about the third point on the benchmark spanning from 4 to 9 qubits, PLN reduces MAE over ZNE and by up to 60%, and for 6 and more qubits, while matching the CDR at 8 and 9 qubits. So the framework is hardware agnostic, but inference efficient and naturally extendable to only noise adaptation also, which will making it more practical candidate for the current NISC work overloads. So of course our codes and everything is available in the GitHub. And so with this, I thank the organizing team for such a wonderful opportunity. Open to questions.
Thank you, Dr. Bala Subramaniam. Can we have the question, please? And can we make it quick because we are already over time?
Ask precise questions. Just unmute yourself and ask your question.
Yes. Can I ask a question?
Sure.
Okay. Just one thing. When you say about the calibration, are you taking consideration calibrating it with respect to the experimental parameters?
You're talking about calibration, okay?
Yep.
Sir, can you please come again?
I'm saying when you're talking about calibration, so
Yes, sir.
are you calibrating it with respect to the experimental parameter, experimental reference? So that's what the calibration is.
Yes, sir. Yes, sir. We are moving over to much more tedious experimental part because initially we started this work only on the simulation side. See, we wanted it to be much more practical, so we are taking that to next level, and we wanted to take that to next level because while doing the simulations, we were able to understand many different and beautiful things. Actually, that is what I was presenting today, and we wanted to be tested or done all these things in the real experimental setup. So that is what, of course, we are moving over to on the higher side actually.
No, but in this particular simulation, in particular work, it has not been taken. Like calibration is not with respect to the experimental values.
No, sir. No, sir. As of now, it is not, sir.
Yeah, because then it can't be this your platform agnostic.
No. Why I said it's hardware agnostic is like because it follows the physics law. That is why, it is a very obedient model. We found this model a very obedient. Like it is not providing some unrealistic outputs because I worked on some other quantum model also, which I got some unrealistic results. So that is why we are telling this as a quantum hardware because if it is obedient, I hope the we can trust the hardware also, right? It's all about model inside.
Oh, okay. So it's only the model because that was the point. Okay. Thank you. Thanks for that.
Thank you, sir.
Thank you, Dr. Subramaniam. Now we can take the further questions later on.
Yeah,
Moving
thank
on
you.
to the next, thank you so much. Moving on to the next speaker, can we welcome Dr. Santoshi Kumari now that she is available? Let's welcome Dr. Santoshi Kumari from Chaitanya Bharati Institute of Technology. She's going to talk about hybrid quantum neural network for medical image classification. Hello, Dr. Santoshi. Can you please share your
Hello.
slides? Hi.
I suppose the previous
Hello,
speaker
ma'am.
has to unshare the screen first.
Ma'am, am I audible to you?
Yeah. But Dr. Subramaniam can, yeah. Yeah, we can hear you, Dr. Santoshi. Here, you can share your slides. Yeah.
Yes. Ma'am, is my screen visible? Hello?
Yes, it is visible, but we can't see the slides.
This is the general, your monitor is
Yeah.
visible. Now it's
Now we can
visible.
see the slides. Yeah. Thank
Yeah, thank you. Good evening, everyone. Myself, Dr. Santoshi from Chaitanya Bharati Institute of Technology, working as an assistant professor, Department of Mathematics. Today, I would like to present my research talk on hybrid quantum convolution neural network for medical image classification. This is the part of my internal seed grant funded by CBIT. So I just want to give the introduction, the methodology, the experimental result, followed with the conclusion. Before I start giving introduction of start talking about my research work, I just want to tell you about what is quantum computing. Quantum computing is a machine which uses the principle of quantum mechanics to perform calculation faster than the classical computers. The basic features of quantum computing includes the superposition, meaning when the qubits not only exist in single state, multiple states. That is the key feature of the superposition. Entanglement. So, what is entanglement? When the qubits are entangled, the measurement of one qubit is interrelated with the measurement of the other qubit. And one more key feature of the quantum computers are the quantum interference. And we know that in the classical computer, the information is stored in the form of the bits, which are represented by zeros and ones. In quantum computers, we store information in the form of qubits, which is nothing but ket 0 and ket 1, which not only exist in single state, multiple states simultaneously, which is also called as the superposition state. The first idea of quantum computing began in the year 1980 by Richard Feynman. He just started that why can't we simulate quantum computers with the principles of quantum mechanics? With that idea, quantum computing came into the picture. Then in the year 1985 has introduced the universal quantum computer. We have a famous algorithm by David Doshi to check whether the function is constant and balanced. Then many more research works foundations are there. So in generally, a quantum system is represented as ket psi, which is denoted as alpha ket 0 plus beta ket 1. So where ket 0 is a column vector having 1 0, and ket 1 is a column vector with the elements 0 and 1. And we can evaluate ket 0 by evaluating mod alpha square. So mod alpha square gives the probability of the 0 state, and mod beta square gives the probability of ket 1 state. And we say that this system is a valid qubit state if norm ket size equals to 1, and we call this is a Hilbert space. So moving on to quantum machine learning. So what is quantum machine learning? It is nothing but the integration of the quantum algorithm with the machine learning program. So when we are talking about quantum machine learning, so we have to integrate the classical data to the quantum. So types of data, we have classical and we have quantum. Suppose we have taken a classical data. If you implement a classical algorithm, we call it as CC, that is classical data with classical algorithm. Similarly, classical data with quantum algorithm. Then we have quantum data with classical algorithm, then quantum data with quantum algorithm. These are the different ways where we can do the research work in quantum machine learning. So why quantum machine learning is very popular? So we know that most of the biological data analysis can be carried by machine learning tools, but the major challenges in machine learning tasks is the computational complexity with time constraints. When the data is very large, the machine learning the time taken by the classical machine learning models is very high. So then in that regard, quantum machine learning plays a promising role because of its principles of superposition and entanglement, which enables to do the task. So it is specially designed for the complex data. So here, with this motivation, this is our first research in-house grant project. So with that motivation, first we have taken a skin data set from the Kaggle, which is available. Online data set having 10,015 images. So we know that skin cancer is very deadliest cancer and affecting people worldwide. Many machine learning models have been designed to decide the accuracy of the model, but the problems face challenges because of the complexity data. So here we have developed a hybrid quantum convolution neural network. That is a model we have developed for the skin lesion classification. So we have taken a multi skin lesion classification having 7 type of classes. So this is a brief model of the classical convolution neural network. We know that classical neural network, given image, we have the classical neural network comprising of the pooling followed by the convolution layer and the pooling, and finally the output followed with the measurement. This is how the classical learning model looks like. Now, this is the quantum model. So, in the quantum convolution neural network, first we take the classical data, we convert them into the quantum state, followed by the quantum convolution neural network. Quantum convolution neural network is nothing but the parameterized quantum gates. We can use rotational gates, that is Rx, Ry, Rz gate, followed by the entanglement. Then after converting the classical data into the quantum state, we use a quantum convolution layer. It is just like the classical machine learning model. We have a pooling layer, then followed by neural network, then pooling layer. Here we use the rotational gates Rx, Ry, Rz gates, and after this we measure it. Once we measure the quantum data will be converted into the classical state. Then we give it for the classification task. So when we are converting the classical data into the quantum state, there are many embedding techniques which can be used to convert the classical data into the quantum state. So the available embedding techniques for converting the classical data into the quantum states are the basis embedding, which represents in the form of the basis state 0 and 1. This is also called as a binary encoding. And we have one more method that is amplitude embedding or amplitude encoding, where we use the concept of normalization to embed the classical data into the quantum states. Then we have angle embedding, which where we use the gates to embed the classical data into the quantum state. So generally for machine learning, we use this angle embedding technique because the data can be stored more effectively. So in our hybrid quantum convolution neural network, we have used this angle embedding technique to convert the classical data into the quantum state. So this is how the angle embedding representation looks like. So here I just given one example of angle encoding. Suppose we have a classical data. So how do we convert this classical data into the quantum state? It is given by, suppose here the data set is having 259. Then we write this as cos 2 into ket 0 plus sin 2 into ket 1. Similarly, cos 5 into ket 0 plus sin 5 into ket 1. Then cos 7 into ket 0 plus sin 7 into ket 1. So the formula for the given thing is x equal to cos 2 sin 2, the tensor product cos 5 sin 5 with the tensor product cos 7 7 7, yielding us the result like this. So we have a data set having 3 points. So finally, after quantum, so it is 2 power 3, we have 8 points. So this is the basic principle of the quantum computing, that is enabling the exponential calculations. So now first, after converting the classical data into first thing, we have taken a data set of having 10,015 images. Then we have done the data augmentation to divide the 7 classes into equal equal classes. For that, we have used this data augmentation technique. Here, we have implemented a two-stage data augmentation strategy to convert this class imbalances. So after using two-stage data augmentation strategy, we have balanced the classes with having each class having 6,705 images. After converting, doing the data augmentation, we are having I just want to tell you the architecture of the QCNN model. So we have taken a skin data set with 7 classes, followed by data pre-processing, then data augmentation. Then we have divided the data into 2 classes. One is training and testing. We have taken 80% of the data for training and 20% of the data for testing. Then we have converted the classical data into the quantum states. We have implemented angle embedding, and we have used PennyLane and PyTorch as the libraries for converting the classical data into the quantum states. And we have carried out this experimental results in the classical CPU and classical GPU. So we have used NVIDIA L4 for the simulation results in the classical GPU. So, and then we have developed this quantum convolution neural network model, followed by the classification, and the evaluation is carried out. So this is how the quantum convolution neural network model looks like. This is fully connected layers with having rotational gates, that is Rx, Ry, Rz gates, followed by the quantum entanglement. This graph represents the angle encoding strategy. Here we used Ry gate to encode the classical data to the quantum state. So overall, our work is taken as from a Hampton 1000 data set having 7 classes. Then we have done data pre-processing. We have used two-stage data augmentation strategy to balance the classes. Then we have converted this classical to the quantum state, followed by the classical feature extraction and quantum convolution and pooling. Finally, we have after the quantum pooling, we have given for measurement, that is done by using poly-Z gate. So in measurement, we have used the measurement metrics as accuracy, precision, precall, and reference score. We have compared our results with the classical available machine learning methods, and these are the results of our developed model. So we have trained our model for 30 approaches, and we have obtained an accuracy of 86%. Initially, when we started our work, due to quantum NISC, we know that most of the quantum devices, what we are doing, have the our noisy intermediate scale. So results were not too good. So we have used optimizers to improve the accuracy. So in this work, we have used Adam optimizers to improve our accuracy, and we have finally achieved an accuracy of 86%, which was very good compared to the previous literatures available. So here, this table represents the comparison of the our model with the available literature survey. So in the method 1, if you see, it is 83%, with precision 81, recall 81, 81%. Similarly, 82, if you look at method 2 and method 3 and compare with our model has given an accuracy of 85.8%, with precision as 97, recall 85, and F1 score as 96%. So what is the novelty of our work is we have implemented this hybrid quantum convolution neural network. The results, the simulation of the results are done in classical GPU, because classical GPU, we have obtained the results in very less time, in fraction of seconds. I did not mention the time measurements here, but what we've learned that quantum machine learning model, when we are doing quantum machine learning task compared to the classical CPUs, I think classical GPUs will be very good, because when you are taking a big data sets, classical CPU, when we look into the classical CPUs, even though we use the libraries PennyLane, PyTorch, Quizquid, the model will take a lot of time in training the data. So I think GPU will be an added weightage. So these results were carried out by in Qubrid AI, who has given us support for us by providing classical GPUs. So uh, 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 So finally, what I would like to conclude is with this work, we can use this work for future things. So with this knowledge, we are already working on one more thing, is that is brain tumor classification, having a 15,000 images, where we are using variational quantum classifiers in improving the model. So this, I just want to acknowledge our college for funding this project. So this project is given by CBIT with a cost of 1,70,000. And my co-invest, I would like to thank my co-PI, Dr. Samson sir, to be a part of this research work. Thank you.
Thank you, Dr. Santoshi. Is there any question? Okay.
If not, I can ask a question.
Yeah, can you make it quick because we are running
Yes.
a bit late? Thank you so much.
Dr. Santoshi, in which particular
Ma'am, can I
problem
close
quantum?
this screen?
Yes, yes.
Yeah.
Yeah, I'm
Yes,
saying
thank you, sir.
which particular brain tumor optimization problem you are addressing with this?
Now with this knowledge, sir, we have started with brain MRI classification.
No, but in
There are
brain
there
MRI
are different kind of brain tumors. His question is which specific type of brain tumor you want to target.
No, actually, we just started with the beginning work is like brain MRI classification. I have to look into the data set. Only the binary classification work is being carried out from our end, sir. Binary classification. But what we learned is we have not used the GPU, but we have tried out with CPU, but the time constraint is more when we were looking into the CPU part. But we have obtained an accuracy of 96% with the by using quantum.
and any kind of pre-processing for data structure or before the classification problem in the current work you have done?
Current work, if you can give me time, sir, then I think maybe I can share you my results, what we have done.
So that you do separately
Because
through
I've
chat
taken the
room.
support
In
of one
chat
of the
room,
students.
you can
Yeah.
share each other's mail, etc., and then you
Yes,
can
yes.
talk separately because we are
Yes.
already running late.
Yes, sir, yes.
And I just have advice, means not a question. Like this kind of meetings are very focused, means where everybody works in this narrow field only. So in future you can stress more on your result and avoid describing what is quantum computing, what is entanglement, etc. Means because this is not a general conference, it's a focused conference. So
Sure,
continue,
sir, sure. Thank you
Dr.
for the
Srinivasan, please,
suggestions
please
and thank you
continue.
for.
Okay. Let's thank the speaker. Thank you, Dr. Santoshi. Now let's welcome our last speaker of this session, Dr. Manik Bhattacharya from Department of EECS, ISER Bhopal. He's going to talk on decoding quantum LDPC codes using collaborative check nodal removal. Dr. Manik, if you can share your slides.
Yeah.
Thank you so much. Hello.
Manik?
Hello. Dr. Bhattacharya.
I think he's in the room but not responding.
Yeah, I think his screen froze and after that he's unreachable.
Maybe there could be some network issue.
Yeah, let's wait for
Yeah, I think we can see him now.
Yes,
Manik.
I
Yeah.
got out somehow.
Yeah, please share your screen.
Yeah. Yeah. Is it visible, the slides?
Yeah, the slides are visible.
Okay. So hi everyone. Myself Moina Bhattacharya. I'm currently pursuing my PhD in Department of ECS ISER Bhopal. And before beginning, I'd like to thank the organizer for giving me an opportunity to present at this wonderful meeting. So my work is on developing a decoder, low complexity decoder for the quantum LDPC codes. And so I can start with some basics to get you on board. So essentially what we need to protect the information that we transfer through communication channel is error correction. So for example, suppose you want to send one bit of information that is your 0 or 1, you don't always send it like that. You essentially, for example, here you use 4 additional bits to encode the same single logical information and you send it. So this is, for example, what is a building block of classical error correction. And you can represent it through certain graphs like this, where basically this 4 represents your bits, which together represents your total logical information, that is a logical 0 that you want to send. And these square nodes are essentially, they does some type of constraint checks. For example, this C0 is essentially a constraint on the V0 and V2. So if V0 and V2's parity are same, then you say there is no error. And if it is not, that is C0 is 1, then you say there is some error between V0 and V2, right? And that is this whole picture, this graph, this bipartite graph is represented by some matrix, which we call it parity check matrix. And essentially, this is your encoding done, and then you want to decode. That is, as I said, there is some error between V0 and V2 if this is violated. And how you decide whether V0 or V2 is violated is what is decoding, right? And so this encoding, that 4 bits of information representing your single logical information, is expressed through the code space, which is basically the null space or kernel of the parity check matrix. And then you have an essential parameter which tells you the capability of the error correcting code, which is basically the distance. And then a good code, obviously you aim for the higher rate of the code. So what LDPC stands for is essentially a sparse parity check matrix or sparse graph. And what it means by sparse is basically the number of ones in either row or column is basically upper bounded by some constants. And for classical LDPC codes, that is low density parity check codes, it so happens that if you have a random matrix, it's already a good code. And sparsity implies there can be efficient decoding methods. And by efficient, I mean low complexity decoding methods. But when it comes to quantum errors, the quantum systems doesn't only get flipped by the bit information, there are phase errors also. And obviously there is a continuum of errors. So essentially, there is a class of quantum codes which can handle the bit and phase flip errors separately. That is, you have a way of identifying the phase flip error through this HX matrix, and you have a way to identify the bit flip errors, which is through the HZ matrix. And basically, there are some things which I will not go in detail into, but essentially, if you have these 2 matrices, they should satisfy some constraint. And this constraint is essentially tells you that, okay, if you have a sparse HX and HZ, then not always give you good LDPC code, unlike the classical cases, right? And similarly, you have distances and you have, as I said, sparse matrices doesn't produce good quantum LDPC codes. But similarly, just like I showed you before, the classical graph picture of error correcting code, you have the same bipartite graph, but here you have 2 independent methods to identify errors. And these 2 independent methods are portrayed in this picture, where basically you have, suppose, 4 qubits. And this set of constraints basically tells you, for example, the bit flip errors, and this set of constraints tells you about the phase flip errors, right? And over the years, people have found good LDPC codes, although it's not trivial. And particularly, I have worked with, so for the benchmarking purposes, my decoder is implemented over the generalized hypergraph product codes, which it so happens that have better performance compared to the surface codes in terms of the resource requirement for same sort of error correcting properties, right? So these are some basics about how you develop the generalized hypergraph product codes. The essential idea that Pantalev and Kelechev worked on is basically The idea is, if you have remember, that I have showed you a commutating that is hz transpose equals to 0. So that constraint, if you satisfy, you have a quantum code. So exactly on those notion, if you want to build a CSS quantum LDPC code, you need commuting matrices. Therefore, means that constraint, and it so happens that you can construct that same. You can satisfy the same constraint to if your Hx, that is the two matrices that is responsible for parity check constants in quantum LDPC codes, have this form. But basically, this B belongs to some ring, which is basically, in simple terms, you can assume these are permutation matrices. That is, there are columns of one, like single one, and rest of the rows are 0. So this kind of columns, and you shuffle them, like there is a permutation of columns is there. And if you construct a collection of those same matrices, you get a bigger matrix of matrices, which is essentially your protograph. And if you lift them, that is from exactly ones and the combination of ones and zeros of those matrices, and you have the bigger matrix is basically your parity check matrix. So now this goes into the what is the quantum LDPC course. Now comes the part where I'll tell you about my work, which is basically improving this particular decoder, improving the performance of the particular decoder called min-sum belief propagation decoder. So the idea is very simple. So for example, if you have this parity check matrix, so suppose this is the parity check matrix. These are like the entries are ones and zeros, and these red entries are basically ones and the white entries are zeros. And this each column represents a qubit, and each row represents a parity check. So if you compare this matrix type of diagram with this particular diagram, so these columns are basically your circular nodes, and each row represents a square node. So if you see, for example, this parity check is this node, so this is connected. So if you compare the adjacency matrix and graph simply, if you have this parity check connected to first, second, and fourth, so first, second, and fourth. Right. So the min-sum belief propagation decoder is an algorithm which iteratively passes message between these two particular nodes, right? So for example, here, what happens is that, for example, if you want to transfer this particular check to data node, right, from this to this direction. So the message passed between this direction depends on the previous iteration's opposite direction message, that is this and this. Note that we exclude any message passed in the direction which is the current message passing direction, right? And this is essentially the expression of the message that has been going through this direction, right? Similarly, the next step is to pass the message in the opposite direction, that is from data to check. And this is the way to do it. This same analogy happens here also, that we exclude any information passed between the same direction, which we take from the previous iteration. And finally, we do this iteratively, like in the first iteration, message to check, then check to message. And finally, at each iteration's end, we take a hard decision, which is basically whatever the message received at this, for example, qubit, data qubit, we take a hard decision, that is, we take the sign of that message. If it is negative, it is -1, then the negative sign we take and we say there is an error. And if it is positive, then we say there is no error. So the technical term is error beliefs, that the algorithms believe that this node has suffered error. That's why it's called error belief. But it so happens that unlike classical case, quantum error correcting codes or quantum LDPC codes has certain structure which essentially gives you this kind of plot. What this means is that basically this is a threshold plot where basically you increase the number of, so for example, here we are using 1, 2, 3, 4, 5, 6 qubits to encode some information, right? So suppose we are using some 3 qubits to encode the same information. Then we use 5 qubits to encode the same number of information and so on. So the idea is, if as you increase the number of qubits, you should get lower error rate. So in this direction, we have lower error rate, and in horizontal direction, this is the physical error rate, that is each individual qubit at which rate they are suffering error. So the idea is, as you increase the size, we should get lesser and lesser error rate. But as you can see, if we apply the same previous algorithm simply, there is no indication of having lower error rates. So this is why it doesn't work for LDPC, quantum LDPC codes. And over the years, there have been many solutions, but they are expensive. So my attempt is towards developing a lower complexity decoder, that is lower time consuming, you can say, decoder. And the reason why this kind of plot arises for simple message passing based decoder is basically this kind of configuration. So this is one of the configuration where you can see. So this configuration is direct result of the parity check matrix for the quantum LDPC course. As you can see, like as I told you that this converts to a graph picture, and in that graph I can have a configuration like this where again you can see these are short cycles, and there are some square nodes which has even degree and some odd degree, right? So I can jump into this part where basically suppose all the square nodes are violated in a scenario, right? And in that scenario, what happens is that, as I told you, it's iterative decoder. That is, there is iteration by iteration processing of the algorithm. So in the first iteration, you can see the decoder predicts that these 3 qubits are like this 3 qubits has suffered error. But in the next iteration, they said it says that there is no error. And in the third, it says again that this 3 has error. So this continues infinitely. So this oscillative behavior tells you that it can never converge. So the decoder cannot conclude which qubits have suffered error. And this is detrimental to the performance of the decoder, and it never ends. Another type of configuration that is inherent to this kind of quantum codes is basically this type of configurations, where you can see there are 2 isomorphic degenerate subsets, which is basically V0, V351, and V405. If you consider this as a set, and then the violet set, 477, 483, 478. So this 2 subsets has identical neighborhood, that is the square nodes neighborhood, right? And because of that, what happens is that this symmetry gives you a similar type of oscillating behavior that the decoder never converges, right? So what we did, we first analyzed the reason of this failure, right? So I can skip the definition and maybe I can start explaining this figure. So what we did, we take one of these nodes, one of these trap nodes, like we say it trap because in this configuration, if it happens and the error happens in this 3, for example, the decoder cannot predict the errors on this 3. So that means that these qubits have been trapped. So we take one of the trap nodes and then we construct a computation tree. That is, so the computation tree represents the exact message passing flow of the decoder. So for example, from V0, it first passes the message of the decoding algorithm to these 3 neighborhood check nodes. Then from that, it passes the message to the data qubit nodes and so on. So what is happening here, this tree basically tells you, based on the parity check matrix or the adjacency matrix of your code, how the messages should be passed in each iteration. So iteration 1, 2, 3, and so on. In this, you can see at some level, there is a node which is again trapped. So if you see here V0, and so this is, I'm talking about this type of structure. So V0 is there, and then again V6 is there. So we get a same trap node again. And this basically we call that this limits the qubit separation. So we call it qubit separation. That is the qubit separation of V0 is 2, because at the third level, we get another trapped qubit. So we proved that if we remove this qubit, you get a scenario where the decoder, that is a simple message passing rule, which is previously was unable to predict the error, can now predict the error. Similarly, if you have multiple strap nodes, for example, here you had V0, V6, and V1. So if you have here V0 at the root, and at this level you have V1 and V6, then if you remove the corresponding neighborhood square node, then the decoder can predict V0, right? So, and another important thing is here, I have written it, that for the whole pipeline, it is not necessary to remove the C6. You can also remove the C5. That is a weaker condition, but it works well with a complete pipeline. Anyways, so this was for the one type of configuration. Another type of configuration that I have shown here, that is this degenerate subset kind of configuration. For this, you can also construct the same. But here, basically, there is a condition, like because of the symmetry, that the qubit separation cannot be improved. But in our work, we have proved that the definition for qubit separation for this degenerate or quantum trapping sets should be modified so that it addresses the similar subset, not the cross subsets. So for example, if we have the blue nodes, you should always look for the blue nodes in simple terms. If you have the violet nodes at root of the computation tree, you should always look for the violet nodes. And if you do that, it turns out, and we have proved it, that there are exactly this number of check nodes that you have to remove to improve the decoder's performance. And what is DV is basically, if you remember, there is a graph corresponding to the error correcting code. So each data qubit node should has DV number of neighborhood check nodes, right? So this is the exact number of nodes that you have to remove to predict, to help the message passing decoder to predict the correction for V0, right? So this is exactly the algorithm, the node removal algorithm. So where basically we first look at all the violated nodes. That's the sole input information of our algorithm. From that, we see for each of the violated node, we construct some computation tree, and we don't need to go, as I said here, if you can see, we can remove the check node from this level. So we address this level and allow this weaker condition allows us to do the same for the other type of configuration. So both the configuration has come together, and we can, so this TT represents, the small t represents the level, and this capital T represents the computation tree. So we can fix small t equals to 1, that is the first level, and from that first level, we'll remove some checks. But we'll not do it exactly randomly. What we'll do is basically first calculate some sort of values, which is the information measurement, which allows us to selectively remove the nodes. And then we can choose this random choosing doesn't because we are, so it doesn't exactly address the quantum trapping sets rather than the classical type of, that is the first one I have shown, because there we don't have exact information of those number of nodes that we want to remove. So this addresses that case, but for the degenerate subset case, this is exact. So this line basically gives you the exact number of nodes that you need to remove. And this is the subroutine, basically where you calculate some values for all the nodes in your graph for the error correcting code, where you first calculate the number of unsatisfied node adjacent to your data qubit, and from that you calculate the same information measurement values for the check nodes. So moving on, now we wrap it up together. So essentially what I'm doing is basically this algorithm will be fitted into a subroutine where basically we first run the message passing algorithm itself, which doesn't work, but we run it to eliminate all the possible errors that can be corrected through the algorithm itself. Then we invoke some another mode where basically the key thing is this part, line number 5, where basically we remove some nodes, check nodes, and then we run the message passing algorithm itself. So it's like first we have a message passing algorithm on the complete error correcting code, the complete graph. Then we remove some nodes, and then we run the same algorithm. By doing this, we are eliminating the possibilities of those harmful configurations that basically doesn't allow you to predict the correct errors, right? So this is what like the essential thing of this algorithm. That is, we first run the main algorithm, which was not good. Then we run this subroutine, which is low complexity, but it removes the harmful messages that was previously preventing us from predicting the correct errors. And then we run the message passing algorithm, because now we are free of the harmful configurations. So we can run the simple message passing algorithm. And what it does is basically this. So before, when I run the main decoding algorithm, for example, so this was run on a particular 88224 generalized hypergraph product code. So what we did is basically standard memory experiment where we started with all 0 state. Then what we did is we applied some noise model, which is the code capacity noise model, where we assume that after all the like error correcting code, like the error correction cycle, we assume that the data qubit suffers some error. And then from that, we measure the stabilizers, or the parity check matrices come into play in simple terms. And from that, we get the syndromes. That is the violated constraint nodes, squared nodes that I have shown. So from that violated nodes, we start decoding. And while we do the simple message passing algorithm, the min sum algorithm that I have shown, so it gets stuck at some iteration. When it's stuck, you can see in this direction, we have plotted the number of uncorrected signal, and that becomes fixed. So no more correction is possible. But as soon as we invoke the sub-decoding round, that is, we remove some nodes and starts applying the message passing algorithm, again we do that. So constantly it starts removing the unnecessary errors that were previously not correctable. And this gives us the confidence that it works, but we again compared. So this is the algorithm which is worse in terms of the accuracy performance for correcting errors. This is the best case scenario, but it is very complex. So it, in this OSD0 decoder has some like matrix inversion step, which is of the order of n cube. N is the number of qubits that you require for the error correcting code. So n cube is still not very much practical because it's very expensive. So our algorithm is not on that part because we don't exactly do the OSD like stuff where we exactly like find the most higher order error, like higher order corrections. But our decoder is simple, but it gives you a good improvement compared to the worst case algorithm that was possible previously. And you can see in this direction the points are not missing. Basically here the out of the numbers. So here I guess we have tried 10 to the 6 Monte Carlo simulations, and there they have found no like all the errors got corrected. That's why there is no logical error. So here we have plotted the error rate, so there is no error. So that's the thing. So we compared we again compared the 3 decoders performance for another generalized hypergraph product code, which is the 127028, and there also we saw the improvement in performance. And finally, as I told you that the fault tolerant threshold plots that I've shown you before. So this is one of the cases for the generalized bicycle code, but this is your ideal decoder, but expensive. This gives you around 24% threshold, while our decoder gives you around 23% threshold. So it's again a little bit less accurate, but the complexity is very good. So overall, the contribution is basically we have performed the simple message passing decoders algorithms performance without knowing the trapping set knowledge. So if you remember, there we are removing the check nodes without knowing the trapping set. So from the knowledge of the trapping set, we have analyzed the possibility of this decoder's improvement. But if you remember the algorithm, there we didn't consider any trapping set configurations. There we are calculating a subroutine call. We're doing a subroutine called information measurement. And from those values, we are targeting the selected check node removals. So this is what one of the important things is, because many of the decoder also addressing this particular case has to know the trapping set configuration. So we have done it without knowing that. And it's a two-mode architecture where we run the same belief propagation or message passing or min-sum algorithm over the same code, but in certain cases we exclude some nodes, that is the check nodes. So this is the two modes, and it relies primarily on the message passing algorithm itself. Therefore, there is no expensive subroutine, as I told you. And the complexity at the worst case depends on the number of unsatisfied check nodes. So, for example, in the generalized hypergraph product code, this exact expression turns out to be polynomial, so which is better than the cubic complexity we have for the OSD0. And yeah, so we have shown the graphs for showing the improvement in the decoding performance compared to the belief propagation algorithm itself. Yeah, thank you. If you have any question, I can answer.
Thank you, Dr. Manik. Does anyone have any questions? If not, let's wrap up today's session.
And let's thank the session chair also.
Thanks so much.
On all the speakers of the session, and we thank session chair and also the session chair of the first session, all the speakers of the first session, and we'll join back tomorrow exactly at the same time at 6 p.m. tomorrow. Thank you all for joining, and all are recorded and in the same YouTube channel. This will be available. So sequentially, if you want to listen a particular talk, you can listen again. Thank you all.
Thank you so much. Good night, everyone.
I think we should left now.